Welcome, everybody. Nice to have you in this webinar. We have 13 attendees at the moment. I see some known names. Hello, Agustina. Hello, Ignacio. Hello, Piotr. And some new people. Welcome to this workshop. We have 3 sessions. I'm going to start to share my screen right now. So we'll have a quick intro where I want to talk about the RCB community, Recovered Carbon Black community, a little bit about me, and then we'll have 3 big sessions. One which is intended as an introduction to Recovered Carbon Black, going deep into what is Recovered Carbon Black, about the process, what do we need to manufacture Recovered Carbon Black, what are important topics. Then we look at the industries, and we'll look at both the furnace carbon black industry and the recovered carbon black industry. And this will go very, very deep at the moment. We have big shortages of product for the furnace carbon black. And so this will certainly be interesting information for you. And in the last session, I highlight some of the possible synergies between carbon black, recovered carbon black, and tire production. So let's talk first about the recovered carbon black community. Smithers and I, we really created this community in the 2018 Carbon Black World Conference. I have to say, back then, the furnace carbon black industry didn't like recovered carbon black a lot, which has changed by now, as you might know. So I did a joint presentation with Peter Terhar in that carbon black conference, and that was the only allowed recovered carbon black conference presentation. And I did a workshop with a panel discussion. I invited some of my industry contacts, and that workshop was really packed with 70 participants, which led to the idea to create a whole conference on its own. That was 2019, the Recovered Carbon Black Congress. And it was a really nice congress with 160 participants. It was one of the best inaugural conferences Smith has had. Then came, of course, COVID 2020. We did an online congress and also an online workshop, because we switched from the conference in the first part of the year into the second half of the year. And we wanted to have the workshop bridging and keeping the energy on the topic high. We had the Presence Conference in Amsterdam last year. You might have heard Michelin Bridgestone announced their collaboration in the RCB rubber project. We also had the online workshop. Now, this year, this is the online workshop. It's a little bit different because we're only 29 days away from the Recovered Carbon Black conference in Berlin again. And I hope to meet you there in person, of course. A little bit about me. So I'm a freelance consultant, 26 years in the chemical industry, including furnace carbon black. I'm doing a boutique consultancy since 2014. I'm a global ambassador voice for recovered carbon black. By now, in my 7th year of consulting, I really work with the whole value chain, starting with, of course, the recycling companies, technology companies, but also investors, tire companies, and the whole value chain. What you might not know is I'm also a certified coach, and I do coaching because I think the changes we need for sustainability, they're not only in technology, they're also in the mind, in the cultures, and our values. You might have seen me on LinkedIn or YouTube, content creation for the chemical industry. I want to show what is the industry like, and I want to go beyond the image of tire recycling, preventing burning tires and mosquito breeding. I think by now, tire pyrolysis and also tire recycling industries really have something to show, have developed products and collaborations, and I want to show that. Enough about me. Let's do a quick introduction about recovered carbon black. Just a quick reminder, if you have any questions, please raise your hand. Please make yourself known. Don't wait until the end of the session or the end of the workshop. Please ask questions. The more, the better. We have plenty of time to discuss. We don't have too many participants either, so please ask questions. That it really is, if we zoom out of all the possible tire recycling processes, and I have to say, for me, tire recycling is tire-to-tire recycling. So for me, really, the biggest or the only valid market for tire recycling is the tire industry. Of course, there's other applications. There is rubberized asphalt, for example. But for me, this is not the circular recycling I'm really interested in. And so for the tire-to-tire recycling, there are three main processes. First, the mechanical, which also is the most commercialized, and we can do shreds, granulates, or powder from either tires or parts of tires. The disadvantage of these materials, unless you do activation and coating, which is possible and done nowadays, we're talking about mainly non-functional filler materials. So displacing a volume of rubber polymer to make the tire product or the rubber product a little bit cheaper. The finer qualities, they are not always available. So the less than 140 mesh quality, or in the mesh, we would have to say the higher than 140 mesh quality is not widely available in Asia, for example. I have in a research study for clients identified 61,000 tons of use globally, but clearly Michelin is the main off-taker. There is already a question. Let me look in the, will we have access to this presentation? Yes, you will get the PDF of the presentation. So I have clicked answer live. We can close the question panel. So back to powder, really the main part of the 61 kilotons globally, I suppose that is going to Michelin. The second process we're looking at is chemical selective recycling. And I'm talking about devulcanized materials. And this could be reclaim or it could be truly devulcanized materials. And we have thermal processes, mechanical processes, chemical processes, and even biologic processes using bacteria. It's clear to devulcanize, we have to get a high surface. So actually the chemical selective recycling follows the mechanical recycling. We have to separate the tires, we have to get the steel out, we have to get the textile out in order to devulcanize. And the highest value is from pure feedstocks. One circle that is working very well is butyl tube recycling. Tubes are just butyl rubber, so it's a very pure material stream that can go straight back into the same application. Devulcanization is more active than reclaim. So reclaim processes typically are destroying the rubber polymer back chain as well. Whereas the devulcanization is a little bit more selective. We could spend perhaps a whole workshop just talking about devulcanization, but the main topic is recovered carbon black, of course. Reclaim is the most used recycled material in all tires. I have identified 134,000 tons, so KTPA is 1,000 tons per annum. Indicating a market of about 205,000 tons. So why that multiplier? So I interviewed 11 tire companies, and their use is 134,000 tons. And these tire companies, they represent 65% of the global tire production. And you can see the companies using devulcanized materials on the right-hand side. We have Michelin, Continental, Pirelli, Apollo, BKT, MRF in India as well, and Trelleborg, OTR, industrial tires. Now we get a little bit closer to our topic, which is the chemical non-selective recycling, because what we do in the first instance with the pyrolysis, we destroy the tire with a high temperature, and in the absence of oxygen, we'll go into details in the next slide. I see two major heating technologies, the conventional, I would say, pyrolysis and the microwave pyrolysis. The difference, I have one slide about the difference. The difference really is whether you heat the material from the outside or from the inside.
Sorry, Martin.
Yes.
Sorry, I have someone asking to speak called Carl Gortz.
Okay.
That's
yes,
okay,
please.
Yeah. Can you hear me?
Yes, Carl, I can hear you.
Okay. Well, I have just one question to the chemical selective material.
Yes.
How do I read devulcanized material? Is it non-vulcanized material which the tire industry is using, or is it really devulcanized?
It is devulcanized because, as you know, the rubber in the vulcanization process, the rubber chains are bonded by sulfur and by polysulfur bonds. And this makes the very specific mechanical properties of rubber, elasticity, rebound, everything. And of course, when we recycle, we cannot just, we have to break these bonds. And these bonds we can break thermally, chemically, and biological. So in the best case of devulc materials, not reclaim, as I said, is mechanically and thermally breaking everything, and the rubber chain length will be reduced, which makes then that the rubber properties will not be at all the same as the initial rubber.
How does the material looks like? What Conti, Michelin, and Pirelli are using? Is it a kind of powder? Is it a kind of granules? Or
it depends on the process. So typically, if you start from a powder, which is very often for the chemical devulcanization, the case, then you will have a powder. Some processes make slab. So then you have a compound slab, just like a mixed non-vulcanized rubber compound. And the slab, of course, is easier to use for the tire industry because they use slab in their own process. The slab is what you get after the Bunbury mixing.
Okay.
But powder is always is also a form of devulcanized material.
Okay, thank you.
So back to pyrolysis or chemical non-selective recycling. We said there's conventional and microwave. Now, I don't see microwave commercialized industrially yet, although I'm very interested because, as I said, the heating is from the inside and rubber is an insulator. So heating from the inside makes a lot of sense in terms of efficiency. Although, of course, the electric power you need is humongous. Again, in the pyrolysis, highest value from pure feedstocks. We talk about the feedstocks in several parts of this workshop. The control of the feedstock, of the end-of-life tire feedstock, is super important for the consistency of the recovered carbon black product. Also for the other products, because depending on the type of tires you select, you might get more or less natural rubber and biogenic material, which is important for the gas and the oil. Recovered carbon black, just broadly, is in rubber very similar to soft blacks. And the soft blacks are 700, 600, and ASTM 500 groups. So carbon black, I have a slide on carbon black, explain you what is carbon black and how carbon blacks are categorized. But these are called semi-reinforcing carbon blacks. And recovered carbon black is in the rubber performance similar to semi-reinforcing carbon blacks. Now, the interesting thing is that of these 11 companies of this study I did, 7 mentioned recovered carbon black is a strategic material because they can put recovered carbon black across several compounds and tire types, so it has a high versatility. However, the available volume nowadays, that study was done last year, but even this year, the available volume hasn't grown. We'll see how I think, and a colleague of mine at Notch Consulting, Paul Eiter, we think the volumes will grow. There will be major growth in a couple of years, but still, it's not a material that is industrially available. There are synergies with Reclaim and in inner liner compounds. So you could put Reclaim in the inner liner, and you could also put recovered carbon black. We talk about applications a little bit later on, but inner liner is the butyl part of the tire, which is responsible for the air tightness, and recovered carbon black it has a good performance in that compound. So tire pyrolysis mass balance. We said tire pyrolysis converts the end-of-life tires into different materials. It really splits the tires into different materials. And we also said the feedstock, the end-of-life tire feedstock type is very important. It could be PCR, which is passenger car radial. It could be TBR, which is truck and bus radial. It could be off-the-road OTR. Of course, in some regions of the world, we might still have bias tires. It could be anything. The important thing is, and every tire, as you can see in the left image, is made of different sections. The tread is one of the predominant sections. Inner liner and sidewall are big. Then it goes into belts and the plies. The plies is where the textile is. The belts is where steel is. So this is showing a passenger car tire, because truck tires don't have the textile, but they have double the amount of steel. And then you have the very small compounds in the bead, apex, and the chafer. Truck tires are even more complex than that, might have up to 14 different bespoke sections. And why is it so important to look at what we are pyrolyzing? Because this is really governing the chemical composition that ends up in recovered carbon black. In this presentation, of course, it's about recovered carbon black, mainly the focus. We'll see the gas is used for the on-site energy creation. The oil back then was mainly positioned as a fuel, a renewable fuel, but nowadays it's more like a raw material, a feedstock for the petrochemical industry. And of course, some of you might have seen that slide in some of my presentations. It used to be part of my boilerplate, but there's one new thing. I'm getting to this in a moment. So typical pyrolysis temperatures could be anything between 350 and 1,000. If you're over 1,000, you come into the range of gasification, and then you don't have oil, and you mainly have gas. This is quite interesting. I don't see anybody going higher than 1,000 degrees, although I do know a company in Switzerland that has a technology like this. And there's a question. Darian, can this fuel be used or considered as biofuel or green fuel? Yes, absolutely. So the biogenic part, as I said, is the natural rubber. And if you want a high biogenic content of your fuel and your gas, then you need to maximize for natural rubber. So you would choose truck and bus tires or OTR tires, which have a very similar composition as truck tires. For example, mining tires, you know, the big oversized 4-ton tires, up to 3-4 meter big tires. They are really, really nice raw material for the pyrolysis, high natural rubber content, and very narrow content of carbon blacks. We get to that in a moment. So truck tires, mining tires, high biogenic content for the oil. And then, of course, the value creation for all products, the oil and the recovered carbon black is high. So back to temperatures, gasification. I don't see anybody industrializing gasification of tires. I'd be interested how the recovered carbon black looks like. I have a suspicion, and I will tell you in a moment when we talk about recovered carbon black composition. We have an inert atmosphere, which mainly is nitrogen. Some processes, for example, auger processes, need only very little nitrogen. Some other processes, like rotary kilns, need a little bit more because the empty space in the reactor is a little bit bigger. Some processes use steam here as an inert gas, which is also possible. And now the new part is about the energy use. And I think this is if you ask me what is the next level of benchmarking technologies in tire pyrolysis and recovered carbon black production, it's how much energy you need for the pyrolysis process. Clearly, we'll talk about the post-reactor process, the milling, pelletizing a little bit later on, and they are also energy hungry, but the most energy consuming part of the process is the pyrolysis, because we have to break up these sulfur vulcanization bonds of the rubber chains. And I use the benchmark of 356 kilowatt hour per ton of tires. And this is, of course, depending on how much steel you have, you will get a different different value. This one is for granulates with already steel reduced to a couple of percent. And this is my theoretical benchmark. Of course, there's no reactor in the world that is 100% efficient. And then we can calculate what is the reactor energy consumption, what is the energy efficiency of the reactor. And I think this will be a future benchmark for the industry. At the moment, I think companies are still a little bit shy disclosing that kind of data, the energy used for the pyrolysis, but I think it will come. I need to click on PowerPoint again. So composition of recovered carbon black. What is recovered carbon black? It's a mixture. It's not a substance, and it's a mixture, first of all carbon blacks that are in the tire feedstock. If you have different tires, the spread of the carbon blacks we'll have in the recovered carbon black will be even higher. If we have, as I said, mining tires, there's two major suppliers of mining tires. We have, limited diversity of tires, of mining tires. And then also the composition is quite narrow and the carbon blacks are quite narrow. Of course, when we go back and we look at the tire, the tread of an end-of-life tire is worn down. So we'll have a little bit more of the carcass composition than the tread. In the new tire, if we pyrolyze new tires, the composition would, of course, be something different. And the carbon blacks could come from a little bit from the tread because it's worn down, as I said, from the sidewall, from the carcass, of course, from all the compounds. And then we have a payload, and that payload could be as high as 25% in European passenger car tire recovered carbon black, because in Europe, a lot of treads are filled with amorphous silica instead of carbon black. Also, for the anorganic content, we could have crystalline silica, which is coming just from sand debris. The end-of-life tires, typically they're put somewhere, not in the cleanest warehouse. They might have been, in the landscape. They might have attracted soil and sand. Some tires are even put underground. So there might be debris. And really, if you want to have a chemical industry product, recovered carbon black, we need to make sure that the feedstock is as clean as possible, and that goes as far as washing the tires and washing the tire granulate before they go into the pyrolysis to avoid crystalline silica. Crystalline silica in Europe is less of a problem. I don't think in Asia either, but it's very high on the radar of authorities in the US. Because we get to milling a bit later on. But when you mill the recovered carbon black, and the milling trend is to ever smaller particles, now we're talking less than 10 microns, 10 micrometers, then that means that the crystalline silica is milled to the same particle size, and that at that particle size, it becomes respirable crystalline silica, which is a toxic substance. Also, zinc oxide and zinc sulfate. What I would expect in the recovered carbon black is more the zinc sulfate, but there might have been high content of zinc oxide in the tire. Normally, the zinc oxide in the vulcanization reacts to zinc sulfate but there might be zinc oxide in the process as well. And then we have two materials in the payload that depend on the process. So we can manage through pyrolysis conditions like temperature, residence time, but also the process type, how much we have of these components. We might have some volatile hydrocarbons. These come from the rubber that is broken down, but is still on the surface. That is the bound rubber around the carbon blacks that's very, very difficult to evaporate in the pyrolysis. And so we might have a content, I put 0 to 3%. It could be much higher than that, but a commercial recovered carbon black should not have more than 3%. An anonymous question, Martin's volume is very low. Could you increase it a little bit? So I hope I can speak a little bit closer to the microphone. Is it better? I hope it's better. Okay, so I'll be closer to my microphone. Thank you. Volatile hydrocarbons. The volatile hydrocarbons on raw recovered carbon black, if you don't optimize the process and you run, say, at 350 degrees Celsius only, and the residence time is not long enough, could be 10, 20%. And you can really smell the volatile hydrocarbons. But this will then not be a commercial recovered carbon black. For the commercial recovered carbon black, we need to finish the pyrolysis, and we don't expect a high volatile content on the recovered carbon black. Then we have fresh carbon, carbonaceous residues, and that comes from the carbonization of rubber polymer, the bound rubber around the carbon black. This is mostly amorphous carbon, although you could argue at higher temperatures there might be some graphitization happening. So amorphous carbon from the depolymerized bound rubber fragments. And this could be anything between 3 and 22%. In fact, this is very much depending on the feedstock and the type of carbon black as well. Now we look at the process and the equipment we need, and we'll clearly see the pyrolysis reactor is not enough. Sometimes I get questions, people say, okay, a Chinese rotary kiln reactor costs only $60,000 or euros. Now the dollar is more worth than the euro. And can we have a pyrolysis plant and make recovered carbon black just with investment of $60,000, $100,000? One question, Vikrant Naik, do impurities or ash also come in because of use in field and on roads? Yes, of course, the end-of-life tires, you will have the debris in the tread still. And if you want to have a good recovered carbon black, again, that debris should be cleaned. And the best stage would be after granulation. Most of the continuous processes and even many of the batch processes don't use the whole tire, but have a shred or granule feed. At that point, it would be good to get rid of the road debris. Darian is asking, when you mentioned finish the pyrolysis process to eliminate the volatile hydrocarbon, what do you mean? Darian, if I may explain you at a later moment, I have a slide explaining what I mean, but really we need to evaporate the volatile matter, and for that we need temperature and we need residence time. So we need time in the reactor. So we have that. Frederic is asking, silicium and zinc are feed dependent. What impact those components may have when RCB is reused to make tire? What management can be put in place? Feed mixing strategy, pre-treatment. That is a very good question. And that, of course, is a question that is also raised by companies that are marketing and developing processes for ash reduction. So not pyrolysis technology companies, but companies that offer ash leaching processes. And so Of course, it is a problem when the end-of-life tire feedstock already has recovered carbon black with a certain ash content. And then we would enrich the anorganic or ash content in the recovered carbon black. At that point, we really need ash leaching or ash reduction technologies. Right now, to reduce the ash, what we can do, we have the leisure of choosing a feedstock or mixing a feedstock such that the ash is not more than a given amount. Typically, and I will get to that a bit later on as well, typically people are now targeting less than 20% ash content. And the reason for that, I will tell you a little bit later in the workshop. But you could do for that, even in Europe, you could mix, let's say, 75% car tires and 25% bus and truck tires, and you will get to that kind of level. I hope that has replied the question. So back to the process, and clearly that process, that is the whole plant we need. And it's a very complex process, which explains why it's not enough to just have a pyrolysis reactor, because we have several steps before the, oops, this is my Wi-Fi antenna going down. We have steps before the pyrolysis reactor, and we have steps after the pyrolysis reactor, quite a bit. And so let's start at the beginning. The end-of-life tires, we need to select the end-of-life tires. One reason is, as I mentioned, to control the ash content or the anorganic content. Then we go in a multi-step granulation. Sometimes it's only the first shred, but certainly for continuous processes, there's a trend to smaller particles. It used to be 20 millimeters. Now really companies are looking at 6 millimeters. Some companies for specific processes like the dripping bed tower process at Pyrum in Germany requires very small beads, which so that they can flow. They actually roll down the tower on the heating surfaces. Then you need a small granulate. And of course, the smaller the granulate, the higher the specific surface, and the easier you can heat the granulate. The worst case for heating an end-of-life tire is if you want to pyrolyze a whole OTR mining tire, 4 tons of rubber chunk with metal, and you don't make it smaller and you don't break it up in small pieces. That will take a lot of energy and a long time for the pyrolysis. Then we are in the pyrolysis, and what comes out of the pyrolysis at that point is a gas, and we can say it might be some 60% of the output of the reactor. That gas in a condenser then can be split into a condensable gas, which we can call oil, which will be about 50%, and that goes into tank or a further distillation treatment, and then the remaining gas that could be 10%. They go in a burner or a generator, and the exhaust you might need to scrub because there's a sulfur content. Some modern processes actually now scrub the gas before it goes in the generator or burner because the sulfur content is also dangerous for the burner. In any case, that energy can be used for giving the energy for the pyrolysis. So most processes actually limit the gas mass flow to exactly what they need in the pyrolysis. It doesn't really make sense to sell the gas, but if you have surplus gas, you could use it also for drying the recovered carbon black pellets. Now, when we go to the raw recovered carbon black, so the solid fraction coming out, which is about 40%, and these are typical mass fractions. Of course, if you run a higher temperature, you would get different things. Certain processes have different mass balances. So this is just benchmarking mass balance. What you would need to do, you would need to separate the metal. In granulate, there can be up to 1% metal still in. If you put whole tires, of course, you have much more metal than that. And the metal you would store and resell. clearly the metal after pyrolysis is not as valuable as if you separate the metal mechanically before the pyrolysis. So the price of the recycled steel after pyrolysis, after the heat treatment, is not as high as the steel price, which is mechanically separate. Then you need to mill the recovered carbon black, because at that point it has a very large particle size distribution, which is between microns and millimeters. There could even be chunks of centimeters. We go in a wet granulation. Now, you might ask, why do we need the granulation? Why do we agglomerate again where we have just milled? That is in order to increase the pore density. And the difference could be whether you send one truck or two trucks to the customer. So if you have a very fluffy material with a very low density, then you need to send two trucks. And the agglomerated pelleted material, you would only have to send one truck. Also, for silo storage, which is done at the tire manufacturer, or for dosing, it's much more convenient to have pellets, granulates. Then you would go into drying, that could be done with the pyrolysis gas, but that really depends then on how much gas you have left after using it for the pyrolysis. Question coming up from Frederick: what RCB milling technologies are usually used? Losses amount. I don't know what you mean with losses amount, but you could use an impact mill with a classifier. That is pretty much the sweet spot. If you go well below 10 micron jet mills, that is the operation range for jet mill. That is ultra fine grinding, and we're speaking of air jet mills. If you go much below 3 micron, and we have to talk about 3 micron of what typically. What is used is the D97, which means that is the spherical diameter, the approximate spherical diameter of recovered carbon black particles, where 97% are smaller than that particle size. So if you go below a D97 or D99, for instance, lower than 3 micron, then we would need a steam jet mill. These are also used, for example, in other industries, pigment industries. Another question coming up from Carl. Frederick, I hope, I don't know what you mean with losses amount, but I hope I replied your question. Carl, why are the prices for steel different pre or post pyrolysis, and how much is the difference? Okay, I'm not a steel expert, but I would claim recycled steel, you get anything $200 or maybe 200 euros if it is separated mechanically and not undergoing temperature treatment. Don't forget the pyrolysis is typically 500, 700 degrees, and that changes the structure of the steel. Steel is cooled down in a controlled way to maintain certain properties. Now, if you heat up again, that changes the structure of the steel, and it has less value. How much? I would say half the value really of that 200. So maybe heat-treated steel, you would get closer to $100 per ton, and mechanically separated 200. Is there significant RCB loss during milling? No, because the fines is the output product. We want the fines, and everything coarser than the fines will stay in the mill until it is grinded and leaves the classifier at the specified particle size to which the classifier is adjusted. Okay, another question popping up. No, that was already covered. So I hope I replied to your questions. The pellets, you could do a whole workshop just about pellets and the hardness of the pellets. But then we have about 39% still in the pellet. After drying, actually the wet granulation, you have 50% moisture in the pellet, and that's the reason you need to dry. And after that, you go into sieving because you want the pellets of a certain size. And the smaller pellets and the larger pellets, they go back actually to the milling and they're pelleted again so that the output of the pellet size is pretty consistent. And then you would pack, and that typically to start with is big bags or super sacks of between 500 kilograms and up to 1 ton, depending really on the density, because a 1 ton carbon black big bag is like 2 meters high and only works out if the density is high enough, the poor density. Darian, sorry, can you explain the wet granulation again? So the wet granulation process, you can do, actually there's a batch process, and you can buy batch pelletizers for the lab. And I always make the joke, these are pretty much like KitchenAid mixes for, dough in the kitchen. They look like, they don't have the same mixes, of course. So you're agglomerating with water and you're making pellets with water. And that's the reason we have to dry again. The industrial processes, they are typically pin mixers. So you enter water and recovered carbon black in a sort of pipe, and you have a rotating shaft with pins on top that mix the recovered carbon black, and the output is again the pellets. Is that like a washing process or mainly cooling process? Are we still talking granulation process? That's neither washing nor a cooling process. Carl, so what will be total capex for the whole system you show in decent quality? You're getting straight to the point, Carl. Of course, it depends very much on the supplier. The one thing is, if you are new to pyrolysis and recovered carbon black, probably you don't want to select a kiln separately and then a mill separately, a granulator separately. You want a turnkey plant. You want a technology supplier that can give you a hand with the engineering and everything. And you get the key, and the plant is already commissioned, and you can just operate the plant. So with that assumption, and not including land and buildings, pre-COVID, I was looking at something 1,300 euros per ton of installed capacity. And then, of course, we have to say, how big is the capacity? Typical capacity nowadays is beyond 10,000 tons of end-of-life tires. Now it's more like 30,000 tons. Some big projects you might have seen, Scandinavian Enviro, are closer to 60,000 tons. If you go to China, they're talking more like 100,000 tons. But then this is not the Western pyrolysis and this process I'm showing here. And that was pre-COVID. What I see now, and back then, of course, there were expensive technology providers with very high quality and everything in between. Back then, maybe pre-COVID, a very high quality pyrolysis would have been 2,000 euros per ton of installed capacity for the end-of-life tires. Now, after COVID, everything is delayed and unfortunately more expensive. So now I think really 2,000 euro for a simple system and 3,000 euro per ton of installed capacity for more demanding, more higher quality system. Many questions popping up. This is a good topic, I think. Is that like a washing? No, that we had already. CapEx we had. Are silos being used as storage? A question from Matt. Thank you, Matt. Yes. And think about, we need silos in between the different steps so that we can separate, for example, the pyrolysis from the milling of the recovered carbon black, because let's say the pyrolysis has a problem and then you would have to stop the whole line. If you have in-process storage and process hoppers, then you can continue the milling until the in-process hopper is empty. So I hope that responded your question. Now we're already 45 minutes. Let me look. I have a couple of more slides. I have a lot of more slides. Is it okay for you to run a little bit over? Normally we would have planned a break, but it would be nice if you could finish the first session. Question from Frederick. So I assume that you're okay running overtime a little bit and making a shorter break. You get more value, I guess. Is the pyrolyzer operated in batch mode or continuous mode? So this really depends on the technology. Both in conventional and microwave pyrolysis, you have batch type and continuous type processes. So a couple of examples of batch pyrolysis is Scandinavian Enviro. I already mentioned them. Ecolomondo, for example. Also EcoTR in Chile. Batch type pyrolysis. Continuous, we spoke already about Pyrum. You might have heard of Black Bear Carbon in the Netherlands using rotary reactors, 2 in series, by the way. It really depends. And then, of course, the question is, which one is better? And that question cannot be answered because it depends on the feedstock. It depends on the geography. It might depend on your budget, what you're willing to spend on the pyrolysis plant. For the recovered carbon black, I don't think it plays a major role. Although I would say the volatile reduction is easier in the batch mode because we can just leave it, longer in. A typical batch reactor is anything between 8 and 14 hours, whereas a continuous reactor, the flow is such that the material has to pass through the reactor. So typically you have maximum maybe 1 hour to spend time for the heating with. So your time to heat is much more limited than in the batch kiln. Frederick, I hope that answered your question. Still one question? No. Okay. So I think we have finished that slide. And this is the process again. And I don't go deep into everything, but just to show important parts of the process for the recovered carbon black quality. And I promised you a sketch of what is it like to heat the rubber in a microwave and what is it like to heat the rubber in a normal conventional kiln. As I said, the rubber granule is an isolator, and when we put energy in the type of normal pyrolysis, it's by temperature. We can actually put a vacuum, then things happen quicker, and by residence time, and also by surface area, so size of the granules. But we're heating from outside in, and that takes a long time. And typically, volatiles are higher than 1.5%. Whereas in the microwave, we're heating from the inside out, and the steel actually helps us because the steel is excited by the microwave radiation, and the carbon atoms are heated, and then it heats from the inside out, and the rubber is bursting because inside they're already, the rubber granules are already cooking and boiling, outside not yet. So that is much more destructive than the conventional pyrolysis. Question from Natasha, what the properties of RCB changed after passed through wet granulation? So imagine a fine powder that is very difficult to handle, Natasha. And the property really is how you can handle the recovered carbon black, how you can store, how much space you need for the storage, how easy you can get it into a pneumatic conveying system, which is used in the tire industry, how easy it flows out of the silo. And one important point, which was confirmed by Pirelli, is that when you put a powder in a rubber mixing mill, a Bunbury internal mixer, Typically, during the mixing process, there is a development of gases, and they need to open the mixer to let the gas out. Now, if you put the powder recovered carbon black in there, and the powder is not completely wetted and already in the rubber polymer, we risk that with the degassing, some of the recovered carbon black powder goes out of the mixer. And then we have a lack of recovered carbon black in that particular rubber compound. And then after that, we might wonder the rubber properties are not as we want them to be, because half of the recovered carbon black went out in the degassing stage. So that is why we need to granulate. We can also do a dry granulation if that is your question, but typically the dry granulation is producing pellets that are much harder. And then again, if you go in the rubber mixing process and the granulates are, the pellets are too hard, they're not broken up, and everything that is not dispersed in the rubber cannot do the reinforcement work in the rubber. And then we have problems again. So wet granulation is important. Second stage in the pyrolysis, here in the pyrolysis process, stage one really is to get rid of all the rubber polymer, to put the whole rubber polymer in gas phase. The stage two is to evaporate all the remaining rubber from the surface of the recovered carbon black. And this is a sketch where I tried to show. These are all polycyclic aromatic hydrocarbons. You can see those rings. So it's very, very important to have a low pH content. We'll get to that as well in a moment. Then ash leaching at the moment is not industrialized. Also, we have to think it's a surplus cost between 200 and 2,000 euros per ton of recovered carbon black to go from 20-25% ash to a couple of percent. The 2,000 is if you want 0.5% of ash. That you wouldn't really do for the tire industry. That would be quite cost prohibitive. Post-treatment, there's also activation, which is also not industrialized, but the concept is that you could get higher reinforcement by increasing the surface area to a surface area which is closer to reinforcing carbon blacks. And then, of course, we have to mill and pelletize. Now, specification, and I won't go very, very deep into that, and I'll tell you the reason. I put this specification up to give a guidance of where I see what the best recovered carbon black can look like. So it's very much like a concept, and the specification is tough. And the first point, consistency, we can only measure from an industrial system. So that really limits the many companies that have a pilot system or maybe even a lab system. How can they get a measurement of their consistency? Question coming up. Could you explain ash leaching process? So typical ash leaching processes are with acid and base. So you're leaching chemically with a lot of acid and a lot of caustic. And then, of course, you need to get the pH right again by washing. Or if you had washed with acid and you then wash with caustic, you might get back to a neutral pH value again. The problem of that process is that typically when you wash with acids and caustics, you get salts, and these salts, they would be waste. At least they have no known commercialization yet. There is one company that claims to have a process that has less waste than the typical acid-based leaching process, but I haven't seen that company industrialize just yet. Is this specification the ASTM standard? No, this specification is my standard. I thought they're still trying to finalize this. Yes. I don't think ASTM Workgroup D36 will ever come up with specifications. I think their main focus really is on analysis methods and standards. And the specification, they will come perhaps from the tire industry. Let me explain that slide a little bit more. Now, in this specification, and of course, any specification where you don't mention the test method is a very, is not a good specification. So having a test method is super important, because only then you can compare apples with apples. And I put here carbon, ash, the char content, volatiles, pH, benzoapirin. We'll get about pH in a moment. Contaminations, milling, pellet hardness, tensile properties. I was talking with tire makers last week about specifications, and I get to that in a moment. And it became really clear that some of these test methods have a high variability, or they're not yet that defined. We need to work much more on getting reliable test methods. For example, how to measure the particle size with laser diffraction. It is not that easy. So if someone uses a test method, it doesn't mean automatically that it's the correct test method, or a test method which has, little span of error and high reliability. I hope, Darian, I answered your question. So click on that question. So the idea for this specification is, in my client work, both with the tire industry and with recovered carbon black industry, was to give them a guidance of what could the best recovered carbon black look like, and then maybe have a second quality, the first one being ecologic and the second one economic. Whereas the raw and unrefined recovered carbon black is RCB-free, has very little commercial value. We'll look at prices in the second session. And then I created the concept recovered carbon black RCB0, which has which is the holy grail, which has the reinforcement of entry-level hard black, the ASTM 330. One question popping up: where do you recommend to test our RCB? That really, at the moment, I don't know where you are, Darian. There is several labs. Some labs have specialized on recovered carbon black and have good experience with recovered carbon black. In Europe, really depends which country you are in. In the UK, there is the Artist Lab that is very well known. They do even benchmarking of more than 30 recovered carbon blacks. So that would be a point too. In the US, maybe it would be more ARDL or ACE labs doing that kind of work. Darren, you're in Singapore. I have to admit, I don't have a go-to lab in Singapore or Asia, but I can, if you contact me, I could make a contact to the Artist Lab in the UK. If you come to the conference, you can talk to them. So the main reason where actually I look at my own specification with a critical eye is it too strict, the RCB one concept? And also there's a couple of points which, I could criticize. So there's very few recovered carbon blacks as of now with proven or published consistency. Boulder Industries were the first in the world to publish about a whole year of measurement of air content and published a white paper about recovered carbon black consistency. That is fabulous. But any tire maker from any recovered carbon black producer needs consistency. And if there's only one thing which is fulfilled in the specification, it should be consistency. If a recovered carbon black is consistently bad, it can be used in the tire industry. Might not have the highest value, but, and there's, of course, some showstoppers, but consistency really is super important. And I have a couple of things like TGA method. Is it representative? It takes 2 hours. Samples are only 30 milligrams. So if you have a whole truckload, that's 20 tons. How can you make sure that that one sample is representative? Char content correlation I'm mentioning here is not approved by D36. So there's a couple of things, and there's new methods now. I quite like the Fourier transformation rheology, which was developed by Conti. and now is finding its way to the ASTM D36 toolbox for recovered carbon black. But the main reason, really, I would say, I would be a critic of my own specification. That is useful if we talk about prices in a moment. But the reason I'm critical about my own work is the RCB rubber project. So Michelin and Bridgestone, they will present more updated and, let's say, the tire industry view specifications for recovered carbon black on the conference in Berlin, November 16th and 17th. And I think that is important, that these specifications don't come from a consultant, however experienced, but they come from the industry, from the tire industry that actually wants to use that recovered carbon black. And let me just say, the collaboration of two arch rivals in the tire industry for recovered carbon black is incredibly positive message for the industry. And at that point, I would say if the tire competitors can work together, the recovered carbon black competitors can work together as well. There's no competition right now. Actually, there's more opportunities for the recovered carbon black industry to work together than actually be competitors. What about coloristic values? Idalo, very, very good question. Now, your surname, I don't know, are you related with Ed? And maybe you work in master batch, but I did a webinar on recovered carbon black for plastic master batch, and I didn't consider plastic master batch so much in this webinar. Sorry, but you can go on my website and you can download that webinar where I even show which color you can expect from which tire feedstock. You are Ed. Nice to have you here. That's great. Good to have master batch people. Excellent. So now we're running 15 minutes over time. I have how many slides more? And then I have 2 slides more. And then we do a break. Maybe we do a short break because some of you might want a coffee or need to have a pit stop. Just to say, give you 2 value drivers for recovered carbon black. And the first one, which we come back to in part 2 and part 3, is low carbon emission. You see, now the world, at least the Western world and the affluent world, is changing from cars that have internal combustion engines to cars that have electrical engines. And when you do the carbon balance for a tire, this is my own balance, which is based on Bridgestone balance. But for some reason, the Bridgestone balance considered only, I think it was 6,000 kilometers life of a tire. And I thought that cannot be true. So I put it to 50,000 kilometers. And it's very clear when you have an internal combustion car, most of the carbon emission of a tire are in the use phase. That is when the engine is running and producing carbon dioxide. Only 10% is in the raw materials, only 3% is in the production. Recycling is only 0.4%. So you would actually focus for an internal combustion car on getting rid of the emissions during the use phase. That has actually led to replacing carbon black by silica in passenger car tread in Europe and part in the US. And now I think it's coming to Asia as well when I hear to my tire friends at Bridgestone and Michelin. Now, Mr. Tesla has excited us all for electrical cars. Now, German car makers are producing electrical cars too, and some have even decided when to stop internal combustion engine cars. And when you simulate, and this is my simulation, when you simulate what the carbon footprint for those is, so I compared for the internal combustion engine car. I took a diesel car, actually a TDI car, Volkswagen Tiguan. I'm German. That's like the car German people drive. And then I took a Tesla. You could say they're maybe a little bit too high end because the Tesla Model S definitely is not a cheap car. But what was important for me is the energy use per kilometer. And then, of course, also for the charging of the electrical car, what is the grid carbon emission footprint? And here I took 231 grams knowing that actually in some places of the world which has more coal-fired power stations, it could be 400 grams or even 600 grams. But even, in that model with these assumptions, which could be changed in the model, of course, now we come to 7% of the carbon emissions during the production and 24% in the raw materials. And this is the reason the tire makers now look at raw materials to have a low carbon footprint, because 24% is something they need to work on, and the use phase is only generating 66% of the carbon emissions. Mind you, recycling is now 1% and is also a little bit more on the radar. Second point is perhaps going a little bit too deep, but in Europe, we have the European Emission Trading System, ETS, and where the industry has been allocated since 2005 free credits for emissions. And those free credits, they are being decreased over time, so to reach carbon neutrality by 2050. And clear in 2020, already the carbon black industry in Europe actually had higher emissions than the credits it received. So the carbon black industry had to pay for its carbon emissions. And that, of course, is also a motivation for the carbon black industry to look at can it help using recovered carbon black or variants of recovered carbon black. I'm thinking of sustainable carbonaceous materials from Birla Carbon. I'm going to meet Birla Carbon on the K Plastics Fair tomorrow in Düsseldorf. Joe Hallett will do a presentation on Continua. Now I forgot the number, but they have a couple of first grades, which is a type of recovered carbon black, but marketed by Birla Carbon, furnace carbon black producer, and of course benefiting from the whole quality control system of Birla Carbon, logistics and technical service of Birla Carbon. So, so much about carbon footprint, PAH. Just to say, furnace carbon black, and typically the furnace carbon black that is replaced by recovered carbon black has a very high content of polycyclic aromatic hydrocarbons. There is low PAH carbon blacks like this one, which is the Cabot LP series, but they are easily 500 euros per ton more expensive than the normal carbon black. And then when we look at recovered carbon black, this is recovered carbon black from a client in Portugal. We can see if you do things right, you have a very, very low content of PAH. In Europe, we are looking at the EU group of 8. These are the 8 PAH compounds that are listed here. Otherwhere, for example, in the US, you might look at EPA of 16, the FDA 15 or 18, or the FDA 22. Then, of course, you get different numbers. Also, there are polycyclic aromatic hydrocarbons that are in none of these groups, and these are very, very high in the furnace carbon black, so that we can say the total content of PAH in furnace carbon black can go as high as 1,000 ppm, and is as higher as bigger the particles are. And the 700 group of carbon black has a very high, a very big particle size. To close that slide, and then we go in a break. To close that slide, all these components, I'm showing here the group of 8 left and right, group of 8 polycyclic aromatic hydrocarbons with a boiling point. And there's one compound, benzo J-fluoranthene, which is already evaporating at 229. The rest is evaporating beyond 400 or close to 500, which, and then it makes sense that most pyrolysis reactors, kilns, are run at 550 to 600 or even 700 degrees. Now, there's one compound which is very, very stubborn for the evaporation, and these are the boiling points at atmospheric pressure. Of course, in a pyrolysis reactor, you might apply some vacuum, you might not have the atmospheric pressure, and then the boiling points are shifted lower. But this one is very stubborn to evaporate from the surface of the recovered carbon black, because it has such a high boiling point. So thank you for your patience with session one. We have overrun by 25 minutes. The next sessions are actually a little bit shorter. Maybe I should have rearranged the sessions. So I would say we take a break and we see each other back in 15 minutes. One question: is pH level in virgin carbon black due to the feedstock type used to make it? No, it's actually more the reactor conditions. You might know that the furnace process, I will explain actually in the session 2. Maybe you can answer that question in session 2, because then you understand how the furnace reactor looks like and why there's more pH in the soft blacks than in the hard blacks. So bear with me, Frederick. Session 2, I will give you the answer. Thank you. Okay, so let's take a break and see you all back in 15 minutes. Okay, welcome back. I hope you had a good break, and we are now in session 2, which is current industry status of carbon black and recovered carbon black. By the way, I hope my microphone level is okay. I've increased it slightly. I hope your ears are not popping out because it is too loud. If so, please tell me. So we will look at carbon black first, because there's a lot of similarities and synergies with carbon black, but there are also some misconceptions. And I believe in order to have a good recovered carbon black, we need to understand carbon black as well. And it's clear that recovered carbon black might develop not so much as a copycat from carbon black, but might develop a little bit more, let's say, the silica way. Silica is a white filler used in tires. It is chemically bonded to the rubber polymer, so it's totally different from carbon black. And it has never really been marketed as a substitute for carbon black, because it provides something very different from carbon black. So let's look at carbon black and what carbon black is and how carbon black is manufactured. Here we see the particle of carbon black. On the surface, the carbon black is a mixture of amorphous carbon and graphitic carbon. And we can imagine the carbon black microparticles, the primary particles, sometimes called nodules, to be spheres like that. They develop out of the oil feedstock droplets. On top of the right-hand side, you can see a furnace reactor. This picture is from Orion Engineered Carbons. And so you put in very hot air, that's the red here. Then you put in natural gas or methane for heating. And then you have a long nozzle, which is injecting the primary feedstock, the heavy oil feedstock. And we need about 2 tons of oil for 1 ton of carbon black. Here, okay, it's more precise, 1.7 ton. That really depends on the type of carbon black we want to produce. But we need a lot more feedstock than carbon black. And then these little primary particles, they grow because the oil droplets, they bump into each other. And so the particle size is increasing as the gas is traveling alongside the reactor. And in order to manage the right particle size for the particular carbon black that we are manufacturing, we need to stop the reaction. And the reaction is stopped with a water quench, which is a very sudden cool down by evaporation of that water. This process, the furnace process, runs very hot at about 1,800 degrees. In order to increase the efficiency and the yield, the industry is now going as high as 2,000 degrees. And they could do so because the cladding which are refractory materials, has been improved to withstand even 2000 degrees Celsius. And so we have a lot of feedstock for 1 ton of carbon black. We have a lot of quench water, 4 tons of quench water per ton of carbon black. And it's not surprising that in the scope 1 emissions, direct emissions from production, carbon black has 2.6 tons of carbon dioxide equivalent per ton of carbon black. And that is really, a good value, because if we don't treat the gas that is separated from the carbon black and get rid of the methane, it would be closer to 5 tons carbon dioxide per ton of carbon black. But back to the primary particles in the ASTM range, they are typically between 10 and 95 nanometers. So this is a nanomaterial, but they're never alone. They are clustered and really fused together at a high temperature into aggregates. And the aggregates, they are very different for every type of carbon black. First question from Ignacio: is D97 a 10 micron spec for agglomerate size? Now, here's the thing, and this is something I still need to finish in the ASTM D36 working group. The particle names are very different for recovered carbon black and furnace carbon black. Furnace carbon black, we have the primary particles, and then we have the aggregates, which are grape-like, aciniform, and they're fused together, and you cannot even mill these aggregates. And then you have agglomerates, which are several aggregates together. And then you have the pellets, which are a lot of these agglomerates together. For the recovered carbon black, we have the aggregate is not fused, but it is the compound of carbon blacks, of the ash, and of the volatile hydrocarbon and the solid hydrocarbon. So the particle size in the case of recovered carbon black is for the aggregates, not the agglomerates, Ignacio. So, and then we have the pellets. This picture is a picture of one pellet on the right-hand side. Carbon blacks have different colors as well, as you can see on the photo from Orion Engineered Carbons. And here you can see some micrograph pictures from a scientific journal article, Nanostructure Quantification of Carbon Blacks. And you can see the nanostructure, you can see the particle, and you can see the aggregate. Now, let's look a little bit at the history of carbon black and the furnace process, because recovered carbon black is often compared with furnace carbon black. And furnace carbon black, about 96% of all carbon blacks nowadays are manufactured with the furnace process, because it is so versatile and can manufacture so many different types of carbon blacks for all the various applications in tires, rubber, plastics, master batch, paints, conductive and non-conductive. It's just impressive how flexible the furnace process is. But in 1830, we had the lamp black process with the feedstock oil. Then the channel process came up in 1864 based on natural gas feedstock. And the particles were collected in so-called hot houses, in the smoke houses. And about 20% of the particles were not collected. So you could see about hundreds of miles and kilometers away, you could see where there was a carbon black manufacture, because there was a large black cloud over that particular town. First carbon black in tires was 1910 by Goodrich. The first gas furnace process was 1920 by Colombian, nowadays Birla Carbon. And really the plant capacity was pretty small in 1923, 400 tons of carbon black per plant. And you can compare that with recovered carbon black. We get to recovered carbon black in a moment. Channel process capacity 32,000 tons by 1931. Then Degussa, the precursor of Orion Engineered Carbons, developed a gas black process with the feedstock oil. And then, of course, we're already in the Second World War. The furnace process with soft blacks on oil feedstock was created by Phillips Petroleum. The first hard blacks, so highly reinforcing carbon blacks, also by Phillips Petroleum. And I believe there's a typo. Phillips should be with 2L. The first hard blacks in 56. First bulk deliveries, so silo truck deliveries, were in 65. 67, the European furnace plant capacity was around 40,000 tons. We can see this. Orion Engineered Carbons has a plant in Sweden, in Malmö. That's about from that time, and that has 40,000 tons capacity. A plant like that in Portugal, in Sines, also by Orion Engineered Carbons, meaning Degussa, has been closed. So that was the plant size back then, 40,000 tons. 1970, the specialty hard blacks like 234 came up. This is also a grade. It's a tire grade, but it's also really, really liked by the coloring industry. Ed, I don't know whether you have used that grade. Typically, master batch plastic industry is not looking at the ASTM name, but you would call this an intermediate super abrasion furnace ISAF carbon black. And then, really surprisingly, the energy recovery, so the conversion of the excess methane gas into heat and, of course, carbon dioxide, only came in 1980. And these energy centers really make the difference in the plant efficiency and also in the carbon footprint, between 5 tons per ton of carbon black and 2.5 tons per ton of carbon black. 2000 came clean extrusion grades, so extrusion, especially body sealing profiles for cars, where the surface has to be really, really smooth, and also non-conductive, because modern cars now are made of steel, aluminum, magnesium, different metals that could corrode if they are in touch with each other. Specialty hard blacks, the 100 ASTM 100 range, super small particles, very high structure, very high surface area, and highly reinforcing, typically not used in car tires, but in truck and bus tires. Then 2015, low pH grades, and Cabot, I think, was the first company that developed this type of grades, used for non-tire applications like food contact, drinking water contact. We get to that a little bit later, because now the tire industry is asking also for low pH content in carbon blacks. Now, last year, the average global furnace plant capacity was 113,000 tons, with, let's say, the old Western world, Europe being around about 100,000 tons, China clearly more than 100,000 tons, 150,000 tons and higher. And well, this year we have a proliferation of many sustainable carbon blacks. I have one slide on that in a moment. So we have now circular and renewable and a whole range of other alternative and supposedly sustainable carbon blacks, including recovered carbon black, of course. So what we can say, the furnace black technology has 80 years, has developed in 80 years. We look at recovered carbon black in a moment. We first look at carbon black markets and what is going on in the carbon black world. But we will see that actually recovered carbon black has already outgrown the very small and slow growth of furnace carbon blacks in its beginnings. So let's jump right into the cold water, let's say. Let's look at global carbon black markets. And you can see boxes, different regions. I've excluded South America because there's nothing particular to say about South America, really, in terms of market shortness, oversupply, or very striking developments. What you can see, two boxes are red, and these are the regions where furnace carbon black and carbon black in general is short in supply. Let's start with Europe. Car sales are down, so the OE part of the tire sales is not good, but replacement is very good. Carbon black demand forecasted for this year around about 1,750,000 tons. There's a supply gap, however, and the supply gap is very big. It's about 670 tons this year. And the supply gap, as Orion Engineered Carbons has shown in investor presentation, the supply gap is actually growing over time. So there might be 760,000 ton supply gap by 2025. The worrying bit is that this supply gap is filled by Russian carbon black. 32% of all carbon black into EU, so European Union, Europe, is from Russia. Even more when we consider Belarus and Ukraine, and then it's 36% of all carbon black in the EU comes from these three countries. And of course, there is worries about the Ukraine crisis and how they affect the carbon black markets. The interesting thing is actually there is no lack of supply. We'll look at imports in a moment. Actually, if anything, imports from Russia have increased because the tire industry is very, very concerned about these supplies stop from one day on the other. You might know a tire line that is not producing costs millions of euros in one single day. So the tire industry is safety stockpiling. I was asking a couple of friends, where does the industry put all the carbon black? Because the silo capacity is very, very limited. And of course, most of the safety stock is in big bags. So, there's a lot of warehouses around Europe with safety stock in big bags right now. Darian is asking, what is RCB market price in Europe or China? Let me continue. Chinese price is on this slide. European price comes in a couple of slides. And let me click, that answer is covered for the moment. I will come to it in a moment. So in Europe, there is no spot volume of carbon black because the tire industry is buying all the available carbon black in addition to their contractual volume. There's a lack of transport trucks. There's an increase in shipping costs, which is another story. In China, actually, the shipping cost has decreased now. But in Europe, there's an increase in shipping costs. There's a lot of delays. There is increased imports, which we'll look at in detail in the next slide. The carbon black industry is running at high occupancy. So the occupancy is how much they produce in comparison with the theoretical nameplate production capacity. And the sweet spot really for the carbon black industry is 80%. Now it's running at 90%. If it if it would run at 100%, actually, that is when material breaks, because most machines are not designed for 100% 24/7 operation. Frederick is asking if the use of carbon black in battery for EV, few percent, but huge market expected, could change the carbon black market. My answer is no, because in all carbon black, the conductive carbon black, and that's not only the battery carbon black, but all conductive carbon black is only 1% of the global carbon black market. So it's peanuts. It's a high value, very low volume market. And for batteries, actually, we're talking about anode and cathode material. And the anode is typically using conductive carbon blacks, but very, very conductive carbon blacks. And the cathode typically is using graphitic material, so neither carbon black. And if you want to use recovered carbon black, we need to get rid of the ash. We need to increase the surface to make it conductive. There were people who have looked at that from an academic standpoint, but really I would rather opt for the mass market in rubber, in tire, than for the conductive market. Because also conductive carbon blacks, you might know, cost anything north of 3,000 euros or dollars per ton of carbon black. up to $20,000 per ton. So it really is a very niche market. Back to ocupacity in Europe. More capacity is announced. There is actually a China synthetic rubber company who is owning Continental Carbon, one of the big carbon black makers globally. They have announced a project for Turkey. I think also Black Cat Carbon is playing with Chinese Black Cat Carbon is playing with the thought of looking at a European manufacturing plant. REACH implications, in Europe, everything needs to be registered with the European Chemicals Agency, ECHA. Recently, carbon black has been identified as a nano material, so all the safety assessments have to be redone, and the risk evaluation has to be redone of carbon black in Europe for REACH compliance. Now let's move to US. Car sales down also much more, 17% forecasted for this year. Carbon black demand a little bit below EU, 1,680,000 tons in this year. Smaller supply gap of 150,000 tons. Less supply, only 2% supply coming from Russia. So you could say everything fine in the US. It is not, because there the EPA, the Environmental Protection Agency, has stipulated compliance with SOx and NOx, so sulfur oxide and nitrous oxide compliance of the emissions of the carbon black industry. So not looking at the carbon emissions, looking at the sulfur and nitrous oxide emissions. And the industry is not compliant, and each of the 5 players had to pay a fine of around about 1 million and had to invest of what they thought would be 100 million, but actually what turned out to be much more expensive. So EPA compliant cost is higher. That puts the carbon black industry in a difficult situation. Also, the conversion actually is delayed. Now, some of the players will not be able to comply until the end of this year, which is stipulated by the EPA in the US. One player is therefore announcing the closure of one plant, but now they appeal because carbon black actually is short in the US, and now they appeal to get more time for their conversion to be able to leave that plant in operation in the US. All producers are sold out. There is no spot volume. So actually same shortness in the US as in Europe. Industry occupancy is about 90%. And there's one player mixing up the US industry, which is methane pyrolysis company Monolith. Many of my former Cabot colleagues are there. They have big plans. They want to have 180,000 ton capacity by 2024. This is produced on a natural gas feedstock along with hydrogen production. And you might know everybody's going crazy for electric vehicles, but also for the hydrogen economy. So this is like a quite interesting proposal, producing hydrogen and carbon black. At the moment, I believe they have introduced semi-reinforcing carbon blacks, not the highly reinforcing hard blacks. So they're playing in the same markets as recovered carbon black. I have the impression that the big plant might be delayed, but I have also the impression that the recovered carbon black industry might be delayed by 1 or 2 years because of the availability of steel. And also, chips for plant control and computer. So US and Europe are clearly shortness of product. Middle East actually is catering for the shortness, at least in Europe. And there is carbon black manufacture in the Kingdom of Saudi Arabia, in the Emirates, and in Iran. Many of those don't have the REACH registration. So the Emirates, I think, is not ASTM material, no REACH. and Iran, 4 players, and not all of them have the letter of access for the REACH consortium of the carbon black industry in Europe. But as we see one slide later or two, in the imports, there is increased imports from Middle East into Europe to cater for the shortness. China is a very funny market. Steel markets are 5% down. And you have to know that the carbon black in China is made on coal tar feedstock. And coal tar is a byproduct from the steel industry. So when the steel industry is down, the volume of coal tar is down. Hence, the price of coal tar is high. That is the case at the moment in China. At the same time, carbon black demand is reduced because the industry is running a little bit slower. Coal tar is very expensive, up to $793 per ton as of 9th of October, so a couple of days ago. There is 77 carbon black plants. Some have closed actually in China because of the scissor situation of a very expensive feedstock and lagging demand. This is very difficult for the carbon black industry. China has been building huge overcapacities. For example, companies like Jingxi Blancat has built over 1 million ton capacity, but they tend to operate this capacity at a very, very low capacity. So the run rate of the Chinese carbon black industry is only 43%, which means that there is, 57% of the capacity is not working. It's not producing, not creating value. So at the moment, China is producing about 3.6 million tons per year run rate carbon black. They could produce easily the double, and they could ease, all shortnesses in the US and Europe. However, the price, of course, is the problem. However, the exports still are slowly rising. There was one instance in 2013 where Longqing exported 33,000 tons to Conti because Conti could not get the carbon black from Western suppliers. Then what you have to know, in China, there's an energy consumption limit for the carbon black plants, which is their way of controlling the efficiency and also the carbon emissions of carbon black. The carbon black plants in China are much smaller, and it's much more difficult to control the overall efficiency and carbon emissions in China. Cabot, having 3 plants, I think 3 or 4 plants even, I think a 4th plant is being built, has increased prices in China by $211 per ton this month. Current prices in China for 700 type are close to $1,600, 600 type close to $1,500 per ton, 500 grade $1,500 as well. So these are all, and 300 is very close, is 1,400. 300 is the entry-level hard black, reinforcing carbon black, but because it is 35% of the global markets, it is the one carbon black that everybody needs. And so because of that large volume, every carbon black maker has a 330, and that has lowered the price. Question, Ignacio, are those prices ex-works? Yes, they are. Ex-works also in bulk. For packaging, typically you have to add some 50 euros or dollars per ton, either for big bag packaging or for small bag packaging, like everything between 10 and 20 kilograms in a meltable plastic bag. So these are the prices. We will see that actually the material that is arriving in Europe is a little bit more expensive than the domestic prices. India, also interesting, 12 carbon black plants. The industry capacity is 70%, so there's some room to grow. Certainly, there's more exports of India into Europe as well. More capacity is announced by Birla, also Continental Carbon, China synthetic rubber company, and Epsilon, who are a steel manufacturer who ventured into carbon black because of the mentioned synergies between coal tar from the steel and carbon black. Indian carbon black demand is reduced. Epsilon is putting in a capex. Interestingly, they posted these figures for $682 per ton of capacity. So this is much cheaper to build a furnace process than to build a recovered carbon black process. So these are global markets, a lot of dynamics in Europe and US, China and India catering for that. China adding more, I would say, nonsense capacity. They have already 200% overcapacity, and they're, three players, Birla, Black Cat, and Songsha Rubber, who are integrated into tire making, are still announcing further capacity increases, which to me doesn't make any sense if you don't export that capacity. Now, these are the imports in the EU. A question, can the imports fill the EU supply gap? We see in 2021, and the year 2021, the import level into the European Union was about 62,000 tons per month. Now that has increased to 74,000 tons per month since the Ukraine crisis in February of this year. And you can see a steep increase in the imports. You can see more blue, that is the Chinese material. However, the Chinese material comes at 2,100, where the price, and this is import prices always lagging a couple of months because of the import-export statistics. So this is June 22 pricing, so pricing from early this summer, where the domestic carbon black had been at 1,885, and clearly imported material from China and India was more expensive. Egypt, that's Birla Carbon at 1,700, Ukraine 1,300. That's the reason of European rubber and tire companies buy Ukrainian and Russian material. These three countries clearly make the cheapest. Other countries, including Japan, but these might be specialty carbon blacks. Just a reminder, these import-export statistics, these prices are calculated by total value over total tonnage. So these are different carbon blacks, a mixture of different carbon blacks. And if there's very expensive carbon blacks imported, like for example, Japan exports only high-value carbon blacks, conductive carbon blacks, this is reflected in a higher price of the other. So more imports into Europe. I don't have the US figures, but I would think that there have been increased imports into the US as well. Let's talk about sustainability and proliferation of sustainable carbon blacks. Proliferation because now we have really a number of sustainable carbon blacks. Of course, leading sustainable carbon black, I would say recovered carbon black. And this is, of course, we've built the community. The industry is going forward. Even the tire industry has recovered carbon black on the radar. The RCB rubber project. The process is pyrolysis, and the feedstock is end-of-life tire ELTs. Then I talked to you about the methane pyrolysis carbon black. There's only one company at the moment. There's 20 companies that are looking at the process, but they haven't figured out how to make the carbon into carbon black, because there's a big difference between carbon and carbon black. The carbon black needs to be the particle size, these grape-like aggregates I have showed you in the beginning. This process is a plasma arc electric process, and the feedstock is natural gas. Of course, the natural gas is anything but natural. However, I have heard that Monolith is also experimenting with biogas. And if you use any biomethane, that would be, of course, a game changer, because then you come in with a negative carbon footprint in the scope 3. Circular carbon black is a furnace carbon black. The advantage is that you can make soft blacks and hard blacks, and the feedstock is tire pyrolysis oil. You use the standard furnace process, which I showed you, and the feedstock is tire pyrolysis oil. Renewable carbon black, again, it's a furnace process, which means that we can make soft blacks and hard blacks. We can make the full range of carbon blacks. And the feedstock is tall oil. For those of you who don't know what tall oil is, you can think of it as a type of pine oil coming from trees. So it's a non-food source, because that's a problem when we have renewable sources. Very often, for ethical reasons, it must not compete with food production. Just to mention, to make a little bit of advertisement for Smithers and myself, I've written a report which will be published soon from Smithers, Technology Forecast for Sustainable Carbon Black to 2041, which is covering these 4 sustainable carbon blacks, because I believe these are the most important sustainable carbon blacks. Then there is wood carbon black made by pyrolysis, and the feedstock is actual wood, so not the oil, but wood. There's, interestingly, carbon dioxide carbon black, and long time I thought this would be direct carbon capture and then go into methane pyrolysis, or maybe making e-fuels and then going into a circular process and to a furnace process. But that would be, actually, I calculated that both routes would actually produce more carbon dioxide than you capture, so it would be pure nonsense. But there is the Sabatier process, and there's one company that is working with Goodyear, and their technology is called Noyes. Mr. Noyes, I think, has died last year or in the recent years, but his wife is promoting this carbon dioxide-based carbon black. I have no information. I'm super curious about that, because it sounds like the holy grail, making carbon black directly out of carbon dioxide. Lignin filler, this is the Suncoal process. Paper companies, Köhler, UPM. In Germany, UPM is building a big biorefinery. Feedstock is lignin, which is a byproduct of the kraft paper process. And this is more like a silica, because it's a very highly oxygenated surface with hydroxy groups. So it's hydrophilic, not hydrophobic. And it needs to be functionalized with silanes, just like silica, for use in tires. Interesting material. And then there's carbon X, which is actually which is using that's a company and brand name, which is using the furnace process, but is making feedstock emulsions, so mixture between water and heavy fuel oil. And in function, they get some sort of filaments and linked filaments out of the process, rather than the grape-like shape of normal carbon black. And this is also quite interesting material. The one thing I would say, all materials using the furnace process have trouble at the moment getting some line space. The sustainable carbon blacks are having problems getting production space on a furnace process, because, as I said, the run rate is 80%. So actually, the material, the furnace processes, they're blocked by the current production, and maybe only in China and India there is sufficient line capacity to make some extra run with clean feedstocks. Vikrant is asking, how is carbon X sustainable? So, I mean, there's different types of sustainability definitions. Of course, if you go for carbon footprint, that could lie in the feedstock. If you have a renewable feedstock or circular feedstock coming from tire pyrolysis oil, I do know that carbon X is also interested in tire pyrolysis oil. So if you cater a sustainable feedstock, that carries on in the process, of course. And then another type of sustainability could be in the high rubber performance, the high reinforcement capabilities of the material, which could increase mileage of tires because of the decreased rolling resistance and the better grip. Go on the website of Carbon X, read their sustainability report. They are tomorrow also on the Plastics Fair K2 2022. They usually go to Tire Technology Expo in Hanover as well. I did a live interview with Daniela Sodi of Carbon X in March or February this year from the Tire Tech Expo and conference. And I hope that replies your question, Vikrant. How do we compare these sustainable carbon blacks? And that's just your question. If we ask how sustainable these materials are, what are our criteria? Of course, carbon dioxide emission in scope 1, 2, 3, scope 1, direct emission, scope 2, energy purchase, scope 3, value supply chain, upstream and downstream. I would always consider also the TRL, because many of these new carbon black types are really very early stages of the technology readiness level, which goes from idea to industrial. Somewhere in the middle, TRL 6 is a pilot plant, for example. TRL 7 is demonstration and large scale engineering. TRL 8 is plant is built. So TRL is of importance because for the tire industry, it's not helpful to have a super sustainable material, but no supply. And, it's only the idea in the head, or there's only a small pilot in the garage of somebody. That is not helpful. Energy efficiency, as I mentioned, I think that is the next big thing for recovered carbon black. Looking at the different pyrolysis processes, I have in my database over 500 different technology companies, not technology, but tire pyrolysis companies, of which 140 are maybe technology suppliers with different processes. And really the question is not only what kind of recovered carbon black these companies can make, but also how energy efficient their process is for making the recovered carbon black. Darian is asking, sorry, what does TRL stand for again? It is technology readiness level. This is a scale actually introduced by NASA, North American Space Association, for the readiness of a technology for space flight. But the chemical industry has adopted the same ladder, again, going from TRL 1, which is idea, to TRL 9, industrial production. So energy efficiency, I think, is the next thing we need to look at for the tire pyrolysis industry. And of course, recovered carbon black needs to find a customer, needs to find a market. The in-rubber performance is super important. And the question is, which of these materials can cover the whole range of carbon black performance, the soft blacks and the hard blacks, and which are playing only in the soft black markets? So at the moment, recovered carbon black is there. The moment methane pyrolysis carbon black is there, whereas circular carbon blacks and renewable carbon blacks can be both soft blacks and hard blacks. And of course, the other carbon blacks we need to also assess what is their performance in rubber. One little tidbit, one little item about the circular carbon black, which is promoted now increasingly by furnace carbon black players, very publicly by Orion Engineered Carbons, and even mentioning recovered carbon black, and even mentioning my specification of RCP1. As good and promising circular carbon black is, because it is made with tire pyrolysis oil, it is linked, it is tied to recovered carbon black, and we cannot actually bash or criticize recovered carbon black performance if we want to sell circular carbon black, because for every ton of circular carbon black, there is about 3 to 4 tons of recovered carbon black that have to be sold as well. So for me, it is not productive to the furnace carbon black industry to actually put recovered carbon black down, because these are two collateral products. Tire pyrolysis oil and recovered carbon black both need to be sold. Ali is asking, when referencing energy efficiency in the benchmarking, are you suggesting the efficiency of the plant producing the carbon black or something else? So remember, now we are 20 participants. I think in the start we were a little bit less, so maybe some of you only started in the middle of the webinar. At the beginning, I showed you the pyrolysis mass balance, and I said that the energy use for typical theoretical pyrolysis, 100% efficient pyrolysis, would be 356 kilowatt hour per ton of the rubber material, the tire material. This is the benchmark. This is the theory. And of course, every real process needs more energy. Some processes more than others. And this is what I'm suggesting, the benchmark, because the pyrolysis is the key, it's the core or the heart of the plant. Clearly, milling is also eating energy. Drying is using a lot of energy because we have to evaporate the water, which is very energy intense. So I think at one point we need to combine all the energy use of the whole plant per ton of recovered carbon black. But to start with, I'm suggesting just to look at the pyrolysis and the efficiency of the energy use in the pyrolysis. Hope that has answered your question, Ali. Then Tim is asking, can the various sustainable carbon blacks be complementary and coexist in a compound? Yes, of course. We get to that in the third session. We're running a little bit late, so maybe I need to accelerate a little bit. But it is actually already used. Blends are used in the carbon black world in the tire industry. Some tire makers blend different carbon blacks to get more consistency, but also cheaper product. And there is companies like big carbon black distributors and transloading companies like Macrochem, who also presented on the last year's Amsterdam Recovered Carbon Black Conference. They are doing blending of recovered carbon black with furnace carbon black. In the end, when you use several fillers in the compound, we need to look at, okay, what performance do we need and what blend do we cater for? These blends could be blends of sustainable material with less sustainable material, where the less sustainable material brings the performance and the sustainable material brings the sustainability. In the end, like cooking, it is, we need to cater for what are the requirements of the compound, both in rubber performance and sustainability. Hope I answered that question, Tim. Let's move on. So we looked at the history of carbon black. Now let's look at the history of recovered carbon black. And you might not have seen this. And both histories came out of my collaboration with the RCB rubber project. And I was asked, how is the evolution of the recovered carbon black technology compared to the evolution of the furnace technology? Now, what I think is recovered carbon black technology is actually developing much quicker than the carbon black furnace technology. Let me explain. So really, tire pyrolysis started in the 1980s, looking only for the oil, and the black stuff that was coming out was discarded. That was the oil crisis, and people were interested basically in a replacement for the oil and the fuel. Sustainability at that point, I don't think was that important as it is now. Back then, actually around 2000, the recovered carbon black was called CBP, carbon black pyrolytic, with a P, not like I put it here, but with a P in the lowercase. 2014, Bridgestone Americas, because Bridgestone is very regional, Bridgestone Americas invested into tire pyrolysis company Delta Energy. That collaboration is still today. They have developed recovered carbon black on the ITEC conference in 2017 or 18. They've presented about use in inner liner and sidewall. That was a good, or is a good collaboration. 2017, the ASTM D36 Committee for Recovered Carbon Black was founded. And there are now, I think, over 100 members in that working group for standards for recovered carbon black, but also for the oil and other things in tire pyrolysis. The first norm of that work group actually is the D8178, which is just the terminology. And you might think, okay, 2 years down the road and just talking about terminology. The norms in ASTM are peer reviewed, so everybody can say, no, I want a different norm, or I don't think it's the right norm. So it's a lengthy process. And also all members of ASTM are not unpaid and they have a day job. So that makes that some of the developments of ASTM D36 take some time. Ed is asking, what is the total recovered carbon black production capacity today? How is it split geographically? Answer comes in one of the next slides, Ed. Thank you. So let's go on recovered carbon black history. Michelin investment in Scandinavian Enviro Systems, now branded as Enviro. That was 2020. Also 2020, BASF investment in Pyrum. Now, BASF, clearly, they're less interested in recovered carbon black. For them, it's a byproduct. They're more interested in the tire pyrolysis oil as a circular feedstock for their petrochemical operations. And they've done nice things. They've done plastic for a door handle in a Mercedes car. They have done, they've produced nylon for an outdoor pant with a German company, VD. So tire pyrolysis is in small volumes already available in consumer products, which is nice. Nice to see that it has found a way into products. Good question, Ed, about the capacity. Capacity clearly is lacking, and BASF, Michelin, Bridgestone would love to have more of the materials. But coming back to the capacity of recovered carbon black, the average capacity last year in North America and Europe of a typical pyrolysis plant has been 3,500 tons per year, which is not a lot. But remember, the channel process plant capacity was only 400 tons per year in the 1920s. Billa last year has partnered with Circtec for recovered carbon black. And I need to correct that. They called it sustainable carbonaceous materials because it is, let's say, more quality controlled material under the Billa brand Continua. What I, together with an industry colleague, Paul Eiter at Notch Consulting, we've written a report about recovered carbon black, prospects for recovered carbon black. That is available, by the way, on my website, a little advertisement. But we have looked at what might be the capacity in 2024. We've also looked at demand figures up to 2030 by region. But if we take this capacity, 13,000 tons 2024, and then we project the same growth rate as furnace carbon black in 2076 at 2% accumulated annual growth rate, the capacity would be 30,000 tons. I think 30,000 tons recovered carbon black capacity will have already by 2030 when I look at the projects that are ongoing at the moment in the Western world. In China, there's big installations. We get to that in a moment. So let's go on. Actually, here is the map of operations that are producing recovered carbon black already now. I will not describe you. You might recognize some of the players: Delta, Boulder Industries, Pyrum is there, Enviro is there on my screen, hidden by the zoom bar. ReOil is the biggest industrial producer in Europe at the moment. New Energy is there. I don't think Möbius in Ukraine are running at the moment for obvious reasons. in Asia, and Restec might be the one company to follow, with 3 plants by now, 2 in Taiwan and 1 in Thailand, which they also manage. Big installations, as I told you, in China, Texan. These are installations of 100,000 tons capacity for end-of-life tires, but very little is known about the quality and the output of recovered carbon black. Frederick is asking, what is the typical valorization of py oil resulting from rubber pyrolysis presented as RCB co-product, even if it's the major product? You know, typical mass balance would be some 40% recovered carbon black, 50% oil. So they're really co-products, and not one is much bigger than the other. You could argue that recovered carbon black has a higher value, clearly over €1,000 per ton, which we'll see in a moment. And the oil, maybe not 1,000, unless it's a very specific oil, like a Circtec oil, which is really very high quality, post-treated. The valorization of py oil, the obvious one is as a fuel, just to burn it. But this is not very circular, right? It's only one time burn, and then we have converted it into carbon dioxide. So as I mentioned, the py oil or tire pyrolysis oil is better used as a feedstock or blend stock. We get to that also in some of the following slides. In material use for things like polymers, like nylon, like plastic polymers, or even rubber, if you want to go back into a tire. I hope that answered your question, Frederick. Carl is asking, what is the difference between black point and white one? Don't really. Can you write again, Carl, please, what you mean with black point and white? Okay. Okay, I see. In this map, don't look at black and white. You could say black are major players with some time in recovered carbon black and with pronounced product development in recovered carbon black, and the white points have not focused so much on recovered carbon black. Yeah, there should be no real meaning between black and white here in the context of this webinar. So that is answered. Anonymous question. I assume that recovered carbon black plant capacity depends on feedstock availability and its transportation costs, and it's also decided in order to optimize process efficiency. Is there an ideal capacity? I think this has to be answered on a case by case. Geography plays a big role in answering that question. Certainly, I will come to the point showing you why we called the workshop to the rescue, because in addition to sustainability attributes, carbon black should also help in places where furnace carbon black is short and not available. Of course, at the moment, the available recovered carbon black capacity is still faint. And so there's a number of considerations: feedstock type, feedstock availability, so how much control you have on the end-of-life tire feedstock, and of course transport. That's like an iteration, because you don't want a long transport for the tires, but you don't want a long transport for your products either. And then the question is, which products are easy to transport, which products might not be easy to transport. I get back to that in the third section in the synergies, if that is all right with you. So now I'm continuing, and I think, Ed, you asked about the growth by the capacity by region. So this is again out of my prospects for recovered carbon black report, with a conservative look at what is the capacity now. and what could be the capacity in 2024. Now, there have been companies, even friends of mine, who have announced like 200 plants by this and this year, and then even 1,000 plants by this and this year. Of course, this is for investors, and this wasn't really for reality. So it's important, all the tire pyrolysis companies have a long list of potential plant installations. And the question really is how much of that can be realized. And here it's important to say this is not my opinion. This is a peer review. So between Paul and myself, with a real critical eye. And at the moment, we wouldn't say there's more than 73,000 tons globally, most of it in Asia, 32,000 tons of recovered carbon black. And again, we're coming back to specifications, because the black stuff that comes out of a pyrolysis reactor is not recovered carbon black. You need the milling, you need the feedstock control, you need the process control, you need granulation, you need so many things to make it recovered carbon black. It's a very complex thing. So there might be people who have announced plants, but what they produce is not really recovered carbon black. It's a low quality carbon product. Tim is chipping in, asking, is there any from the slide before that has good TPO enough to use as DEF fuel? Now, I don't know what DEF fuel is. And again, I would recommend material, not thermal valorization for the oil. But the sad thing is the oil really, you need even higher quantities than the recovered carbon black. So you need to really stick with major players. And the oil, let's say, from Pyrom is really spoken for, because Pyrom is selling to BASF, and within the Black Cycle collaboration, a part of that goes as carbon black feedstock to Orion Engineered Carbons. So that is spoken for. You might be lucky, Tim, I don't know where you are. You might be lucky with ReOil in Europe, with Enrestec in Asia, Delta Boulder in the US. And the others, are really, really small quantities. And I hope that covers that question. The main point really here on that slide is significant capacities will be built. And so significant that in 2024, the availability of recovered carbon black could be 331,000 tons per annum. And most of the capacity, not in that petrol blue Asia, but most of the capacity actually in Europe, and more precise in Benelux between Rotterdam and Antwerp, where are the big chemical parks in Europe, and where there's a lot of synergies between feedstocks, tire pyrolysis, and also a petrochemical industry for the oil. So this is really Benelux chemical parks are a hotbed for tire pyrolysis industry at the moment. And one word of caution, because of the difficult availability of steel and also computer controls, it might be, and even ancillary equipments like mills and granulators, it might be that this capacity doesn't come all on stream in 2024. It's very difficult to exactly predict. Many of these installations might be delayed by a couple of months, maybe even up to a year. So that capacity maybe doesn't come in, sharp in the year 2024. And again, cautious estimate, only looking at major players and not looking at companies that take their mouth really full and promise a lot. The gray bars, if you ask yourself, that capacity, global capacity for recovered carbon black, is about the same size as the demand for N600 group carbon black in Europe. And then the N700 would be the smaller bar. That is just a comparison of the volume. Okay, legislation, one more thing about recovered carbon black, and it's really important to look at REACH. I've been actually crafting material safety data sheets declaring recovered carbon black as a mixture. Also, if the volume is small, that might still be okay. If your volume gets over a certain level, over 1,000 tons, it's really, really difficult to justify mixture. You need to either REACH register, or you need to make sure that you can use the sameness approach, and you can use the furnace carbon black REACH number and registration in Europe, because every chemical material needs to be covered by REACH in Europe, and the tire makers, they will ask for that. And so I can't really preempt the thing, but there will be one super important presentation about REACH and recovered carbon black in the conference in Berlin in November 16th and 17th. That will be very, very important for the industry, especially, of course, because REACH is Europe, especially for the industry in European Union. USA, respirable crystalline silica, we talked a little bit of that. In all parts of the world, there's the challenge of declaring the end of waste. In the European Union, on country level, the end of waste for tire recycling products is in Spain, Portugal, and Italy. And if it is not declared on the country level, actually you can go on the county level, which, for example, a friend of mine, a neighbor of mine close to Berlin, running a big company for rubber granulate, the company Genan. They have a factory very close to my home. And they had to apply with the county of Brandenburg, which is around Berlin, for the end of waste status of their end of life tire rubber powder. And they got the end of waste. Generally, the end of waste can be declared when you can show that there's a market and application. But the end of waste by industry experts is regarded as a little hurdle. You need to be able to have the end of waste, because you cannot expect your tire companies to have a license to treat waste. If you don't have the end of waste, your recovered carbon black is a waste. And then everybody buying your recovered carbon black needs to be a waste recycling facility, which generally a tire production, of course, is not. But when you can show the market and the application, and that there's a commercial value and use of your product, then you can get the end of waste. Documentation, there's so many things, and maybe with this webinar you understand how complex the whole industry is, and what you have to be compliant to. The material safety data sheets in the European Union need to be localized to the countries. Now, for the US, it's easy. There's one national language, it's English, maybe a second language is Spanish, but then you have covered everything. There's many more languages in Europe. And so I'm at times consulting with tire companies that want to buy recovered carbon black, or, for instance, sustainable materials. And they, if I ask samples from my contact companies producing recovered carbon black, this company needs to have a localized material safety data sheet, which is not in English, but it could be in Italian, or it could be in French. And, not many companies in the recovered carbon black industry have produced Italian and French material safety data sheets yet. So this could be also a pinch point, a pain point. Now, someone asked for prices. Here are prices. These are for European Union. Chinese prices, I have already mentioned some slides before. Chinese prices were discussed in that slides. And so here we are looking at European Union carbon black pricing, Russian import carbon black pricing, and recovered carbon black pricing. And here you also see the usefulness of specifications, because for my RCB1 top of the line specification, I'm using 80 to 120% of the N660 price, which in November is around 1,354. Prices were going down again because the oil feedstocks price goes down again. So the recovered carbon black in my pricing model follows the carbon black price. Of course, if you're producing recovered carbon black, you could decide you don't go on a tracker with carbon black, but you have a consistent price independent of oil. These are strategic decisions. But if you ask what is the recovered carbon black price in relation to the carbon black price, this is one way you could look at it. Then, of course, RCB2, which is not fulfilling RCB1 specification, which is more an economic than an ecologic product. I would say November, some 600, 700 euros. RCB3 is not to be commercialized in rubber. It's just a burning value of 30 euros per ton. And then you understand why the milling and the wet granulation and the drying is increasing really the value so much, to magnitudes more, to 2 magnitudes more than the 30 euros per ton. The interesting thing is, so different carbon blacks, these pricing equations, these are price models with different base prices for different carbon blacks. The lines are parallel because they all depend on the same oil feedstock. Of course, the true market prices might be different from one supplier to the other, and one might favor one grade over the other. This is a price model. But what you can see, a steep increase after Ukraine crisis. Here, by the way, you can also see the effect of COVID, of the rubber industry slowing down in the year 2020 and going up again, building up capacities again. Ukraine crisis, steep increase because the oil price increased. Now it went down again in June. In June, I have some reference prices for the carbon black imports from China and from India. And now prices are going down again. Russian, you can see why people are interested in Russian carbon black in Europe. Has always been the cheapest carbon black you could possibly buy, and all the tire makers are buying Russian carbon black. They would love to continue buying Russian carbon black, but now they're also in an ethical conflict of interest. But they cannot really replace that high volume, especially if Chinese imports and Indian imports are so much more expensive than the Russian imports. So it really is a squeeze for the tire industry. It's very, very difficult. And again, this is something, if we only had more capacity for recovered carbon black could surely come to the rescue. Now, do you have pricing questions still, or do we do a break? Maybe ask a question to the Smithers team. Should we do a shorter break and then continue the third section? The third part of the workshop is a little bit shorter than the two parts, and we'll talk about synergies. What is the best timing for you, the participants, and the Smithers team? Please, could you give me some feedback? 10-minute break from Alice. Okay, let's have 10-minute break. Everybody get a coffee. And we go to the third section after 10 minutes. So not 50 minutes like on the slide. We do a 10-minute break, and we'll have a good third session about synergies with carbon black, recovered carbon black, and the tire industry. Thank you all, and see you in 10 minutes. Okay, welcome back to the Recovered Carbon Black workshop, to our third session. And the third session is about possible synergies between carbon black, recovered carbon black, and the tire production, and actually other industries. And again, please chip in with questions. If you still have questions from the previous sessions, don't be shy. Ask me questions as I go. So the first thing really about the synergies is the first value driver, the carbon footprint. As I've showed you about electrical vehicles and also the situation of the furnace industry, the carbon emissions of the furnace industry, there's a need actually to do something, and that need can be catered for by the recovered carbon black or largely by the tire pyrolysis industry. So tire producers, carbon black producers have committed to reducing their carbon footprint. The tire producers are now developing sustainable raw material profile portfolios, including recovered carbon black, and as I mentioned, also including the now many different alternatives of other sustainable carbon blacks. On the carbon black side, I've told you here is now the product name I was looking for, Birla Carbon Continua 8000 sustainable carbonaceous material. That is a type of high quality recovered carbon black made by Circtec and marketed by Birla Carbon. And Birla Carbon, you can download the sustainability report. They're using tire pyrolysis as one means on their path to carbon neutrality. I think even Birla and also Cabot have pledged for net zero, and you might know carbon neutrality and net zero is not the same, because for carbon neutrality, you can just buy credits, or you could just plant trees and, you know, you do some bad thing on the left-hand side and you do some good thing on the right-hand side, and you meet in the middle at zero. That is not possible for net zero. Net zero means no emissions, full stop. And for that, as you can imagine, and for the furnace process to be net zero, some innovation is required, or some alternative materials like recovered carbon black, which, by the way, is also difficult to see to reach net zero, but already it is less carbon footprints than furnace carbon black. So on the path to net zero, it might have a role, but then we have to think, how can we do a pyrolysis with zero carbon black emissions? Maybe if we're running an electrical system, maybe if that electricity only comes from solar and wind energy, that would be one possibility. And then we need to see what we do with the gas, certainly not burning, because that would arise a carbon footprint. Just telling you my thoughts on how the tire pyrolysis industry could become net zero. So how do we measure the carbon footprint? And that brings me to the topic of LCAs, life cycle assessments. And it's clear you cannot do this from your pilot plant in the garage. This needs to be from the industrial plant, from the whole industrial plant as well. There's two norms, the ISO 14040 and 44. They date 2006, and they govern all the LCAs. Now, I want to tell you clear message. I'm not a friend of life cycle assessments that are mainly based on carbon dioxide avoidance. And they go like this. Our shiny silica is helping in the tire, is helping saving carbon footprint by increasing rolling resistance, by increasing grip. And so there's less carbon emissions from the use phase. That is not a sustainable material for me, because when you consider silica is actually a high carbon footprint material in production. So I like the view which is more transparent, and maybe it's because I'm an engineer and I'm not, usually working a lot with ISOs and life cycle assessments. But I think much greenwashing can be done with life cycle assessments if you base it on avoidance, especially if if the product you're comparing to, you can make it really, really bad, and then you look good. To me, that is clearly greenwashing. What I want to see in a life cycle assessment is what are the actual emissions of the plant, so the direct scope 1 emissions, and the scope 2 power purchase emissions, and the scope 3, as I alluded to many times in this workshop, and that is transparency. And with sustainability, we really need transparency. That is super, super important. And we need, of course, honesty. And we need companies that have a high emission, not to falsify that emission footprint, but to say, yeah, we're bad, but this is the path to getting better. And then this company is credible, in my book. There's a little picture from Birla Carbon for the KE Plastics Fair. So they will actually do a mini conference on their stand tomorrow. Joe Hallett, I think, is it 9 o'clock? No, I think it's on the afternoon, 1 o'clock. So anybody, I don't know what the chance is that anybody of you is close to Düsseldorf, but Birla Carbon will present on their carbonaceous material portfolio tomorrow on the Plastics Fair in Düsseldorf, Germany. Second value driver, we talked about polycyclic aromatic hydrocarbons, PAH. And I told you, generally, this requirement comes from food contact, drinking water, rubber gaskets. Maybe also there's some rubber used in toys. There's a German GS, geprüfte Sicherheit label for toys, which is very restrictive because generally, kids put anything they play with in the mouth. So it needs to be safe. Same, at plastic master batch industry, one large part, 30-40% of plastics use is plastic packaging, and food packaging is predominant in the packaging. So there might be food contact packaging. You need to be low in the benzoapyrene level. There's some other specifications. In European Union, there's now a unified food contact regulation. Switzerland is different. US is different. US is actually magnitudes more difficult to achieve. There we're talking about parts per billion, not parts per million benzoapyrene in the plastic material that comes in contact with food. Of course, there's even more stringent, more strict regulation for medical plastics, but I'm not touching here because I wouldn't think that recovered carbon black goes into any medical plastics. But coming back to tire industry, obvious that is the largest market for carbon black and hence for recovered carbon black as well. It's very obvious that tractor tire, agricultural tires come in contact with soil, and that soil is where we have our food production. So it makes sense that ag tires are monitored for PAH. However, there's an increasing demand even for car tires, so PCR, passenger car tire radial, because now the big pink elephant for the tire industry, or let's say the frog they need to eat, is not so much ensuring the proper recycling, which is still a challenge. But now with tire pyrolysis, there is, I think a good path indicated for the tire industry. But their major problem is road wear particles. When we say an end-of-life tire is 10% lighter than a new tire, these 10%, they end up in the environment, in the air, in the water, in the soil, and they become, these are microplastics. And now everybody's attention, at least the authorities' attention, is very high on microplastics. So now the tire industry, even for car tires, is looking to limit the PAH value of the raw materials going into compounds. And that's the value driver 2 for the recovered carbon black, where actually there are synergies between the tire industry, the non-tire rubber industry, and the plastic master batch industry, where really recovered carbon black can be the solution. Process integration. And sorry, these slides are text heavy, but these are like the brainstorming slides of the workshop. And there's not many pictures because many of these things have not been realized, so that we can show some pictures, or they're super secret. So let's consider the scenario of a tire pyrolysis at a carbon black producer. This would be nice because the tire pyrolysis oil could be used as a circular feedstock like Oran engineered carbons, or a blend stock. So feedstock is 100% use, and blend stock is if we say we're putting 30% pyrolysis oil to a carbon black feedstock oil, fossil oil as normal, to the carbon black production. And this is the model, the Black Cycle model, where you might know Black Cycle is a European Codis funded, European Union funded project. Michelin is leading. Alyapur is collecting tires. There is and also preparing granules and shreds. Pyrum is the pyrolysis company, and there are some distilleries and petrochemical companies. And then Orion Engineered Carbons makes circular, sustainable furnace carbon black out of the tire pyrolysis oil. Of course, the potential for sales is either blends or direct recovered carbon black. For example, as Birla Carbon does, but calls it a different material, sustainable carbonaceous materials. Then tire pyrolysis at tire recyclers. There's one question. Let me look at it. Oh, there's several questions. Wait, it looks, one is open. Okay. Frederick, if tire pyrolysis oil is used for carbon black production, very little CO2 reduction is therefore expected. You know, the tire pyrolysis oil carbon footprint, I don't have a number in my head, but if you have an Excel spreadsheet or calculator with you, I would calculate per ton of recovered carbon black, I would calculate 600 kilograms of carbon dioxide per ton of recovered carbon black. And you need to divide it by 40% and multiply it by 50% because that is the mass balance for the oil. And then you get the footprint for the oil, which is less than 1 ton carbon dioxide per ton of oil. So I think it's still pretty good compared to fossil feedstock. But clearly, it is not as good as a renewable feedstock, which will go in with a negative carbon balance because in its lifetime, it has actually captured carbon. And that negative footprint, of course, is not in the scope 1. The scope 1 is likely the same as the furnace process because it's manufactured in the furnace process. But the negative carbon footprint would come in scope 3. So I hope that is answered. Randall is asking, what is the CO2 equivalent per ton of recovered carbon black? Yes, that is exactly what I said. So it depends, of course, on the process. Do you have like 2 pyrolysis kilns, one after the other, like Black Bear Carbon, to have a super high quality recovered carbon black? Then your carbon footprint is slightly higher. I think you can, with a range of technologies, you can take 300 to over 600 kilograms of carbon dioxide per ton of recovered carbon black as a approximate figure. Depends on the process, and also depends, of course, on the post process. Depends on if your pyrolysis is electric again, and my considerations for net zero for the tire pyrolysis. If your process is electric and you have green electricity, then of course your carbon footprint is pretty low. That's like a interesting technology to me when you want to reduce the carbon footprint. Now going back to the slide, I've always actually indicated in presentations starting from 2017 that there are synergies between different tire recycling methods and technologies. We had that topic right at the beginning when I talked about mechanical recycling, selective chemical and non-selective chemical recycling. There are synergies, and it all starts with a smart deconstruction of the tires. Now you might ask, what is smart? It is to be defined, TBD. But one idea of a smart deconstruction might be we really separate the different sections of the tire, which are glued together by the vulcanization. So it's not going to be easy, but this is the smart deconstruction, because then if we have the sections pure, within one section, we have a very defined chemical composition. And then we can say, okay, this is a nice material. This is the fillet of the tire. It goes into devulcanization, and everything, the carcass, can go in the soup for the pyrolysis, and we recover out of the pyrolysis what we can. But for me, the hierarchy would be, if you have a pure material like the inner liner or tubes, that would go into devulcanization. And the pyrolysis really is the most forgiving tire recycling process, which accepts textiles and steel. And the carcass, if you can't separate really the carcass and the plies, it would make sense to go in the pyrolysis. And so that's what I'm indicating here. Thread could be powdered and devulcanized, and then, carcass is missing pyrolysis. Carcass could be recycled by pyrolysis. That's the missing word here. Then also a case I have looked at tire pyrolysis at petrochemical companies, and that could be, it wasn't my case, but it could be BASF and Pyrum. So you could have the treatment of the tire pyrolysis oil on site. One trouble, let's say two troubles for the tire pyrolysis oil. One is extremely low flash point, which makes the transport quite difficult. But if we have the tire pyrolysis site within the conglomerate of the petrochemical industry, within the refinery, then the transport is no problem. Flash point is no problem. Sulfur might be a problem, depending on the mass balance and the technology of the pyrolysis. Of course, the higher the temperature, the more the sulfur will go in the gas, not in the oil. Actually, the sulfur in the carbon black is really tied to the process type. I don't think that by residence time and temperature you can change a lot, but certainly the sulfur balance between the oil and the gas, you can work a lot by a fast or slow pyrolysis and a low temperature and high temperature pyrolysis. You can tell the sulfur where to go, and you want the sulfur in the gas because then you can just scrub it out, and the oil will be low sulfur. That is the value determining factor is the sulfur, in addition to density and the kinematic viscosity. So that could be process integrations. Blending. Now, here's the value driver 3. And back to the topic of the workshop, to the rescue of carbon black. We have a shortness of carbon black, so blending or extending could be a really nice synergy. Now, you have to know that the furnace carbon black industry is already bleeding. Now, bleeding coming from blood is like, the idea is little droplets of material. And now, of course, the furnace carbon black industry also has faulty material, which is quality tested and doesn't comply to the specification, and it is separated. And but they put 1 to 4% of this out of specification material into each and every carbon black, and the tire makers, they don't really see it, because at that percentage you don't really see a high impact of any non-conforming material. If you consider the global carbon black market, this bleeding market, that could be a market of 552,000 tons per year across the globe. The only trouble is it's already used by the carbon black industry for their non-conforming, their non-compliant material. Also, it is a no frills and low impact application. Just hiding dust under the carpet. This is really not motivating the recovered carbon black industry. We want to be there in higher addition rate. We want to show the sustainability. We want to have a high quality recovered carbon black, which doesn't need bleeding, but blending. Now, blending, you could argue, goes anything between 10 to 50%. And then, I think ultimately, really, we want to sell 100% recovered carbon black product that has a high performance and high sustainability credentials. But the recipe could be blending with furnace carbon black. You might have seen on the Recovered Carbon Black conference last year in Amsterdam, Igor Levenberg, the owner of Makrochem in Poland, who are the biggest transloader, I think globally even, who are really moving more than 300,000 tons of carbon black, a lot of it being Russian carbon black. So he has presented about blends. I have the impression from recovered carbon black producers that tell me they have sold recovered carbon black to carbon black producers. Now, what would a carbon black producer do with recovered carbon black in quantity, not only for lab testing, but in quantity? So this suggests to me that there's already being blends catered by other carbon black producers who might not have published about this, or might be a project specific for a client that has requested a confidential project. It's a quick fit solution to the carbon black shortness the blends are. And the deal is that the sustainability credentials come from the recovered carbon black, and the controlled rubber performance comes from the furnace carbon black. I think it's an interesting thing in the short and medium term. Again, and long term, I think the recovered carbon black industry wants to sell 100% product. Of course, and just as I mentioned, some tire makers, I'm thinking of a French tire maker, are known to mix different furnace carbon blacks for quality optimization, but also for economies optimization, so for pricing, cost optimization. And you can imagine this a little bit like those of you who like to drink wine. You can have a single grape is every year different. So a carbon black can have a variance in quality, even though it is in the specification. But a cuvée, a wine that has several grapes by their vineyard, can be made such that it tastes each and every year, where the grapes are different, but each and every year the cuvée tastes the same. So you could, by blending, you could even out differences and variations in the quality, even of furnace carbon blacks and including recovered carbon blacks. And you could make sure by a blend that it has always predictable performance. And this is one of the things the tire makers want from recovered carbon black. They want to be recovered carbon black to be a reliable, consistent material. And again, to that metaphor of the wine cuvée, a blending would be one and, let's say, quick way of achieving that. Logistics. Now, this is my favorite example. Imagine a tire pyrolysis at a tire maker. So what is nice is generally with recovered carbon black, we look at the end of life tires. So we look at consumer tires that are there at the end of life, but the tire makers, they also have industrial waste. They have tires that are non-conforming, non-compliant. They have in-process waste. So that could be directly recycled in the tire pyrolysis at the tire maker. Then, this is my favorite point. The truck deliveries of new tires go to the service point, to the garages. Now, these garages, for every tire they sell, they take in one tire that is end of life. So they could actually return to the tire company where we have the tire pyrolysis and therefore tire recycling facility in the same truck. And the volume should be similar because for every new tire, we have to take in one old end of life tire. And so reverse logistics, I like that a lot. Also, some furnace carbon black silo truck deliveries could return to carbon black companies loaded with a silo delivery of recovered carbon black. So actually, that would be another flow. You might know the silo deliveries of carbon black, they are quite expensive. And although sometimes stupid deliveries are made over thousands of kilometers, typically a silo delivery is not cost efficient if it goes over 500 kilometers. And that is because the silo truck is coming back empty. However, if the silo truck comes from the tire maker, where we also produce recovered carbon black, with a load of recovered carbon black, that would be at least some of the trucks could be filled on the way back. There's, of course, a disproportional volume because there will be much more furnace carbon black going into the tire maker than the volume of recovered carbon black could flow back. But, if we really put it to the extreme in the optimization of logistics, that would be one possible model. Tire pyrolysis at carbon black producer or transloader, and transloader in that case would be Macrochem. So there we could make big bags of blends or pure recovered carbon blacks, on the same truck to rubber companies. So let's say a rubber company, tire company typically take in silo deliveries, but smaller rubber companies might take big bags, and then the carbon black maker or transloader distributor could send a truck with a number of recovered carbon black big bags and a number of furnace carbon black big bags in one delivery. Or the recovered carbon black could participate in the existing logistic infrastructure for the silo trucks delivery from the carbon black maker. So I think there's a lot of synergies to grab with logistics combined with blending and the value points I already mentioned. And that was really it. That was the workshop. There's still one question from Tim. How do you see the economics being impacted if going the blending route versus selling directly to the tire manufacturer? Now, okay, I don't have hard figures in that case, Tim, but to me, it is clear that companies like Macrochem, they will not pay, 1,700 euros for the recovered carbon black, because they want to make money as well. And they see if they deliver the quality control and the blending and the rubber testing, and they actually make the guarantee to the tire maker that this blend is performing in a certain way, they will actually want to buy the recovered carbon black, not at the highest price, but they will be very, very cost conscious. So if you are a recovered carbon black company, certainly selling 100% directly to the tire manufacturer, to me, sounds more profitable. But then again, in life, very often we have to have mixed strategies. And there might also be, strategies in different phases. You might, to be able to move material, the blending might be of interest, and you can move some volumes by blending, and the price may be not very attractive, but at least you're moving material and you're producing, and you can gain more experience. And as I mentioned, I think I see the blending as an intermediate phase in the marketing of recovered carbon black, which could be a quick drop in for the tire makers, also catering for the shortness, which we have now. I don't know how long the shortness will endure. I hope, the troubles will end. Both the Ukrainian crisis will end on our side here in Europe, and also the EPA compliance struggles in the US. So we don't know how long the shortness will endure. But for me, the blending is a quick fit. It might not be the value fit. So I think that the last session, we have a lot of time open still, but I still, I hope you have more questions on what we have discussed on either nature of recovered carbon black from the first session, on recovered carbon black market situation and furnace carbon black market situation from the second, and then the synergies in the third. And synergies, as I mentioned to you, is a bit more like what I see from my consulting work, but also like where I see the industry going as my very own vision for the industry. Ignacio, thank you for another question. Can you repeat the D97 10 micron spec for agglomerate size and which types of silica are not desired? Okay, so let's go back in the presentation to the slide where I had my my specification, which was here. So that is my own view of the state of the art of recovered carbon black. To be honest, there is almost no company that is fulfilling this specification. Many companies come very close in many regards, but some companies, as I mentioned, the consistency has to be proven on the industrial system. So 10 micron milled particle size. Here, I'm saying laser diffraction, ISO standard or the ASTM standard. We now know we need to define more, and that is in the comments. So laser diffraction, we need to specify it's a dry laser diffraction, not in the liquid medium. Also, the pressure is very important. Here, the industry standard seems to go into the direction of 2 bar. And also then there's a different algorithm because the laser rays are diffracted, so they change their course, and the algorithm is calculating the particle size with the assumption that the particle is a sphere. But, as I've shown, neither carbon black nor recovered carbon black are spherical particles. So it's an approximation at best. And there is a work item in the D36 group, which is working on this laser diffraction particle size method. But, this is what I defined with the means at hand I had. That's, and the D97, to repeat, this is the material, the spherical material corresponding to 97% smaller than 10 micron. Nowadays, I would say maybe it's a bit harsh. There's maybe 20 micron is good enough. The problem I have nowadays, what I'm thinking now with the D97 is it means a 3% can be above 10 micron, and the 3% can be anything above micron. They could be 100 micron, and that is a risk. So, which is why I tend to think, although the D99 has a higher error in the determination, I like more only to have 1% open than 3% open. So much about the 10 microns and the particle size measurement. The other one question from Ignacio was about the types of undesired silica. Now, you could argue silica as a whole is undesired for sure in Europe, because if you want to get below 20% ash, so that we could argue for the short term with the sameness approach under REACH that we have a carbon black, not a recovered carbon black. There is a type of carbon black that is allowed to have 20% ash. So, and then, if we fulfill, and that's not the only condition we have to fulfill to have the sameness approach with carbon black. There's other items we need to cover as well. But so the ash level, the general ash level needs to be considered. And then, of course, the silica is a major part, certainly for Europe, the amorphous silica. And it's the same like with the carbon, where we can have amorphous carbon and we can have crystalline or graphitic carbon. Silica is also in both modifications, and the precipitated silica, which is added as a filler, a high-performance filler for the tire treads to provide lower rolling resistance, higher grip. Unfortunately for the tire, also the wear rate go up. The wear rate of the tire goes up, so the longevity of the tire goes down if you use silica. But in Europe, the US, and increasingly in China, the tire industry is using precipitated or amorphous silica as a filler in the tread. And the undesired silica compound is the crystalline silica, which is also known under the name sand. Sand coming just from road debris and either from the use time or from where the tires have been stored. And sand, when we mill the recovered carbon black ultra fine, under 10 micron, the crystalline silica under 10 micron becomes a respirable crystalline silica, and that has a cancerogenous effect if you inhale it. Of course, you would never inhale that crystalline silica coming from the recovered carbon black, because the recovered carbon black would be used in the tire, would be bound in the rubber matrix. But both the European Chemicals Agency as well as the US authorities, they use what is called the precautionary approach. So they're not interested in the material that can go out of the tire. They're interested in a total content of dangerous and potentially toxic or even cancerogenous materials. So the European ECHA is limiting PAH in, for example, rubber granulates now, not the PAH that can go migrate and can go out, but the total content. And the same approach is being taken in the US for the crystalline silica. So Actually, no crystalline silica is allowed, or there is a very, very small ppm rate of crystalline silica that is allowed in any material, because they argue if it is a powder and if it is inhaled by production staff, then it could be potentially cancerogens, which, like all nanomaterials are cancerogenic. This is not linked to the substance, but this is linked to the particle size. I worked 14 years in titanium dioxide, the white pigment, which is at the walls around of all of us, and they had a big ripple because it was declared a nanomaterial. Titanium dioxide is typically milled in jet mills to less than 1 micron. So the nano part of the titanium dioxide is even higher. And that has caused classification as 2B, potentially cancerogenous in the European Union. So more questions. In Amsterdam, Brits and Michelin mentioned 10% substitution in the future. Do you think they get there? Yes, and sorry, and just to finish, Ignacio, I hope I covered your question. New question from Tim. Amsterdam, Brits or Michelin mentioned 10% substitution in the future. Do you think they get there? Yes, I do think, Tim, they will get there. But also, you have to understand how the tire makers think. They don't think of recovered carbon black as the only tool. They have a whole toolbox of all the sustainable carbon blacks. And also, remember, in a tire, there is more polymer than there's fillers, which means that now there is actually an increasing content of natural rubber in tires, because natural rubber is a biogenic material. Of course, there's some ethical problems because of the small hold production of natural rubber. That's a whole different topic. We go to a workshop on this. So the tire makers, when they say sustainability at 10%, they have a whole toolbox with the polymer, meaning the rubber elastomer, with all the fillers, the black fillers, the white fillers. They have the additives. So for them, it's really the sum of all the actions. And as I mentioned, 7 of 11 tire makers, representing 65% of the global tire production, say recovered carbon black is the most promising material to help them get to their sustainability goals. So hope that answered your question, Tim. Ali is asking, you provided your sustainability benchmarking, which is fantastic. You have a calculator or specification that you could use to measure these benchmarking values, i.e. CO2 levels in scope 1 to 3 or in rubber performance. I think, Ali, thank you for your thanks. I think, regarding a calculator or specification, I might have data. I'm doing some estimations for tire makers or for brands. At the moment, I'm working with Decathlon on sustainable materials for for bike tires, not car tires, but for bike tires, and because they're really, really focused on sustainability and not only looking at recovered carbon black, but the whole portfolio of sustainable materials. And it's very difficult because with every supplier, I need to do an NDA with that consulting client, because typically these are data that suppliers, recovered carbon black makers, or even furnace carbon black makers don't share very openly. So it's very difficult to have like a quick fix in a calculator or even in a webinar like this. There's too much confidentiality around these data. But on a case by case and introduction to companies, that could be done. But very often these companies require NDAs. And then if you have, let's say, a small company and a big company involved, it's very difficult because, the one has a big legal department, or even it's worse if there's 2 big companies and they have 2 legal departments that are really fighting each other for the NDA. So it's not easy because of the confidentiality of the data. It's not public data. Carl is asking, RCB1 spec, what level are current available RCB grades compared to your spec? That's a very good question. And as I mentioned, and it goes in the same direction. I might have some data and I might have some privileged knowledge, which I cannot share because I want to value my confidentiality, non-disclosure agreements. It's clear I work with many, many companies, but I cannot share information when I have NDAs. So difficult to share. I can give ranges, which I did for the carbon footprint. There's, as I said, there's many companies that really are in the scope of RCB1, and that might not hit RCB1 because of one little thing of my own defined specification, because it's not in the focus, or maybe they just don't have the test device at the moment in their lab, but they could very easily get to that, if they invested in that test equipment. So in the same question I get asked by clients, and then again we come back to non-disclosure agreements, and I can generalize, I can show you the general trend, and I can share you where the industry is in general, but I cannot really disclose company data. Tim is asking, do you think the L to RCB market will be fragmented or more oligopolistic with a few winners? That's a good question that is being asked by consulting clients as well. It's clearly the production figures I have, and Paul Eiter from Notch, we have put up in our report. They are considering major players, and many of these major players have 10, 20 plants planned. I don't think, as I said, 200 is any realistic. I think the speed to market is of importance. I think technology players have to be industrial by 2025. If they're not, others will actually take larger parts of the cake. However, still, I would say it's El Dorado time, and now actually collaboration between different technology suppliers is really of the essence, because the specification is not cast in stone yet, and there's approaches from my side, there's approaches from RCB Rubber. REACH is not in dry towels yet. Please watch the presentation of that company on the Recovered Carbon Black conference in Berlin. That is super important. So it's difficult. I like to think that there is not an oligopoly, because that would also be, to the extreme, there could be one or two companies, but then actually the risk for the market is very big. Because then if those companies fall over, which has happened with a company called pyrolysis, that, at one point was perceivedly leading the market with a site in Germany and a site in the US, and being super duper, and they had really a very, very knowledgeable technical director who still works in the industry, fortunately. But the company went down despite all of that. So I really hope, and I think the industry needs to have diversity and different technologies, also for the risk management. And as a bonus answer, I don't think there is a best technology, and usually I tell people there are best people, and people check the people whether they're reliable. Check the people whether you can work with the people, whether they can be trusted, whether they respect you, whether they are a good partner. Because if you work in the long term, the tire pyrolysis and recovered carbon black industry is a young industry, and things will go wrong. Factories will fall over, and then you need the people to correct for these shortcomings. Even from the superstars, the companies that are in the news all the time, they haven't found, the Holy Grail either. And you really need to ensure to work with the people, who then make the technology work with you and for you. Tim, they said 10% RCB specific. And that is about the RCB rubber Michelin Bridgestone. Yes, absolutely. I think, yes, we have some rough edges on the specification, on the consistency. But yes, I do believe. Generally, if a company, even Pirelli says they want to have 3% sustainable materials by 2025, it's, as a first assumption, first of all, they're very interested in recovered carbon black. They're in contact with many players. They haven't published anything about use of recovered carbon black or any partner. But if the company has a sustainability goal, I think that percentage, if you take that percentage of their carbon black use, that is that's a good objective for recovered carbon black. So, 3% of the carbon black Pirelli buys, in my very own estimation, would be a fair use for recovered carbon black, to replace 3% of Pirelli furnace carbon black with recovered carbon black in order to achieve their goal, along with other materials, of course. So, generally the tire industry is not very openly publishing what exactly they use, or let's say which addition rates they use. You might have seen Enviro Michelin publishing about recovered carbon black in racing tires. Why racing tires? They're high performance, but racing tires have low production numbers. And that's what they can do with recovered carbon black, because they cannot get enough of Enviro recovered carbon black to go in a full commercial tire. But now they've presented a commercial tire that is roadworthy with recovered carbon black from Enviro. Of course, they wouldn't tell you about how much recovered carbon black is in there. They said a percentage of sustainability. I think it was 43 or something. They presented two tires, one truck bus tire and one one car tire. And the car tire contains recovered carbon black, and the truck bus tire, I think, contains a sustainable carbon black. So furnace carbon black from tire pyrolysis oil or renewable oil. But they would never tell you exactly how much recovered carbon black is in the tire. So the 10%, I hope that replied. Tim is asking, what's your thoughts about continuous or semi-batch? Again, I would say choose the people first, then choose the technology. You want to see a running industrial installation. From your technology supplier, you want engineering services, or even from a third part, you want engineering, EPCC, engineering, procurement, construction, and commissioning. You want a turnkey. You don't want, to buy all the equipment yourself and do the engineering yourself. Mind you, the engineering will cost you 1 to 2 million for a normal plant, tire pyrolysis plant. So actually getting the engineering, the pre-engineering study done, that's already, you need to have decent money. Then continuous semi-batch, there's use cases for both. I'm a chemical engineer. I probably would err a little bit more to continuous, because I like continuous systems and the scalability. There are reasons for batch as well. I wouldn't bash batch technologies, especially semi-batch, because semi-batch for me means discontinuous for the mass flow, but continuous for the energy flow. So if we're cooling down one reactor and we're heating up the other reactor with the cooling heat from the first reactor, that is, that would be my sort of batch system. And then consider SUV tires or luxury car tires, which nowadays are all self-sealing. So we don't have the fifth tire in the boot anymore. We want a big space in the boot. So we have the tire with a liquid rubber self-sealing. These tires cannot be shredded and they cannot be recycled. Actually, on the technical data sheet of those tires, you will find the remark, this tire cannot be recycled. And one way, of recycling would it to put the whole tire in a batch kiln, be it conventionally heated or even better in a batch kiln that is microwave heated. And that is the only way without cutting the tire and, invoking the self-sealing liquid. That would be, the only way to recycle self-sealing tires. The same industrial waste of a tire maker, tires that are not vulcanized yet. They're very gooey. If you put them in the shredder, they even block the shredder. They don't shred into nice materials. You will have spaghetti instead of granules coming out. And then you cannot handle those spaghettis. And those unvulcanized tires, but they are fully built, they are difficult to recycle as well, because they cannot be mechanically granulated. Those you can put in a batch pyrolysis very easily, and this would be maybe the only way of recycling unvulcanized full tires, unvulcanized materials, and the self-sealing tires. So it really depends on what is your feedstock, where do you get your feedstock from, how big do you want to build your plant. But remember, choose the people first, then choose the technology. And I hope that replied the question, Tim. Any more questions, Smithers team? How are we looking time-wise? I don't have any idea what we planned. I think the third session was a little bit quicker than the other sessions, but I want to give you more, the participants want to give you more opportunities to ask questions if you have. So Smithers says all good. So all good means we can continue for some minutes if there's questions. But there don't seem to be questions. So to the participants, now we have, how many participants left? I think 16, no, we have 15 participants. Some have left already. Last opportunities for asking questions. So 2 more questions. Frederick, thank you. Thanks a lot, Martin, for this excellent, very detailed workshop. It's a pleasure, Frederick, and hope to meet you on the conference. I meant to say in the last slide, please register for the conference. Today you had one expert, on the conference you have all the other experts working for you, presenting for you, answering your questions. The conference will be a good one. Thank you, Frederick, for asking your questions, and my pleasure to answering. Darian, what is your contact email? I think if you take my name, in the logo of Wolfersdorff, and you Google me, you will find my email, or connect with me on LinkedIn. My email is martin@wolfersdorff.com, or connect with me on LinkedIn. It will be a pleasure. Thank you, Darian. Tim, Black Cycle alluded, attention, half of EU tires going into that process in 25 to 26. Can that happen? I think this is not what my understanding is. I think what they say is they want to recycle half of the tires, which is about half of the EU tires, which is about 1,500,000 tons, because half of the tires are valorized in thermal recovery, not in recycling, and they want to get that into a recycling loop. And they also say 6 years after the Black Cycle project end, which ends in 23. So 23 plus 6 years for me is 2029. And then, add 1 year. So really what they're saying is half of the EU tires by 29, 2030. Can that happen? I think it will be quite difficult to get half of the tires, because clearly they find someone doing something with them right now. And at the moment, everybody is happy and making money with the gate fees. And this is a bit of a problem in the EU. There is not a lot of pressure to go into the material recycling versus the thermal recovery. And also, every European country has different collection systems. Many actually have managed systems. Germany is a free market. I did a market study this year. It was super difficult to really identify the whole value chain for the end-of-life tires in Germany. But getting hold of the tires and really getting hold of half of the tires in Europe, that could be a difficulty. I would say by then, Michelin is a really powerful tire maker. And by then, it's not only the 13 parties of the Black Cycle project, but they will have partnered with many more companies within the 6 years after the project. And I really believe in partnerships like the RCB rubber partnership, the two tire competitors working together, focused on recovered carbon black. I think the same can happen in Black Cycle, other tire makers coming in, other pyrolysis companies in, building ecosystems. And in the end, when you think about it, all these ecosystems, they need to connect at one point so that actually we have one overarching ecosystem. And with that kind of thought, it could happen. Will it be easy? I don't think so. Because there's, the more people you have in the boat, the more interest you have, and half of the tires are, is 1,500,000 tons of tires is a lot. But I think with dedication and with strong partners, it can work. And I would, I want it to work. I like the idea that it is working. The only, grain to finish on the Black Cycle, the only grain at the moment is they don't appear to focus on recovered carbon black all that much. They want the oil for Orion engineered carbons for sustainable carbon black, and they want the oil for the petrochemical industry. Is it for wax or a certain oil? I forgot exactly what the product is. Now I'm moderating the next Black Cycle workshop in Zaragoza, which will be the week after our Berlin conference. And I think that workshop is open to the public. So if you're interested in Black Cycle, come with us to Zaragoza. The workshop is free, but they're not paying your hotel or something. So you can connect with the Black Cycle people and ask them these questions. And I really hope Black Cycle in the future, certainly for recycling half of the tires. So imagine half of the European tires, 1 million times 40%. If that all goes into pyrolysis, that's a lot of recovered carbon black. They need to get recovered carbon black into the product mix at some point. Otherwise, that will not happen. EU, okay, that was just a comment, Tim, EU else, of course. So, okay, I hope I covered that question about Black Cycle, Tim. Now we have 14 participants. Maybe Smithers team, time to close the workshop. What do you think? Are you participants happy with the workshop? Let me know. Contact me after the workshop if you have if you want to anonymously ask me more questions, or if you need help. And as I said, please sign up for the conference to get more than one expert. Okay, thank you all. And, last but not least, thank you, Smithers team. You're just great. And it's really great to be a business partner with you, running workshops and doing conferences like the RCB conference. Many thanks. Thank you. Bye-bye.